the eta, I don't know what's happening with the chalk. Then I have the eta of x plus 1 minus eta of x. Okay? And now you stare at this thing, and then you see that, you know, I can better interchange, I mean, you know, the order here, then I get the minus sign, and then you see that I get a discrete conservation law. I mean, the function which is sitting here is just exactly this, up to the minus sign is exactly the same function as over here, shifted by 1 unit. So it's a discrete derivative which is appearing in this expression. And so you know, I want to write this in terms of currents. So here I write the current from x minus 1 to x. And here it's the current from x plus 1. But now I have interchanged this, so I put this minus sign here, right? And so from this you can read off what is the current function. So that's, of course, important point, the current function. Which is then, according to our notation, is simply the jx x plus 1 is then, I mean, it's a rather intuitive object, C1 eta, and then I have eta x minus eta x plus 1. I guess that's, I hope I did this correctly. Yeah, that's the minus sign, yes. Okay. And so, you know, you could ask yourself, you know, what what would this mean, sort of, you know, I mean, these are just sort of functions which are evolving, so there's in some sense some average going on, but you know, you can think about what this really means, and this was something which was sort of asked already, you know, yesterday. I mean, in terms of what it means is that you know, I look at this empirical current between x plus 1, but I just look over this in a very short time interval, and I condition on a very particular configuration, right? I mean, so I fix my eta, that's the eta which is appearing over here, and I ask myself, you know, how many particles are jumping to the right and left on average over a short time interval. And this is nothing else but this function gx x plus 1 of eta dt, right? I mean, that's sort of the meaning of that function. Okay, so that's fine. So now we have already a result. I mean, so now I can look at eta of x at time t plus, and now let me just sort of write this as okay, sorry. We want to look at the ddt of eta of x of t. And yeah, here I left out the t argument, but now I put it in, and then we have discrete derivatives. So let me write this sort of like a partial. I mean, that's just sort of a notation. Just means, you know, the function at the point x plus minus 1 minus the function shifted by 1 unit, and so we have here then a plus, and then we have here the j x plus 1. Just sort of make sure that I do the correct indices. Okay, at time t, and now I put here the delta in front. I mean, so that's now sort of the discrete derivative. So it's this function minus its shift by 1 unit to the left, and this is equal to 0, right? I mean, so this is basically what I computed. And this is sort of true for any, you know, these are functions of the configuration, of course, and that's true for any configuration. I mean, because the conservation law is always valid. And so once I have this equation, then of course I can sort of do averages here. So this average is now in the initial state here, right? Because I put the t over here. So this is an average over the initial state. Then I can put the averages over here. And whatever initial state I do, this kind of discrete conservation law is valid, right? Yes?
So what is the first step? Second,
This one here? Well, okay, so this means that I'm fixing the configuration eta. The full configuration I'm fixing. And then I'm computing the empirical current for a short time interval dt. So, you know, imagine that at time t equals 0 I have fixed, and then I go for a time interval dt, and then of course, you know, some of these exchanges will have happened already. And but now what I do is sort of, you know, I take a very short time interval and I do average now over my random waiting times, right? And then the assertion is that, you know, for a short time interval, the result will be given by this formula here. So it's just sort of emphasizing, you say, I have to distinguish between what I mean, the current function, which is this function which I've written down, which is a function on, you know, here you, okay, so maybe you put here the eta here, I mean, you know, for every configuration, this function is defined, right? And the empirical current. And so in terms of the empirical current, which is doing this counting, it's actually already an average over a short time interval. Yes?
Earlier the superscript was supposed to mean the value after the jump, right? J plus 1.
Yeah, here's
no, that eta x superscript j plus 1.
Yeah.
But now that in the next line, this eta x minus 1 is it before the jump?
No. I mean, so I'm carrying out this sum, and
no, that's saying, yes.
And I'm saying that there are only two terms appearing in this sum. One is where j is equal to x minus 1, and the other one where j is equal to x.
Yes. So the first time would then be eta x minus 1 superscript x minus 1 x.
Yeah, so the first term is j equals x minus 1. So x minus 1 is sitting here, and then this one becomes x.
Yeah, that's okay. I'm just
then if I do this difference, I mean, this one becomes eta x minus 1, and this is just saying eta x.
So the superscript somehow...
No, there's no superscript. It's just, you know, I mean, you know, I'm just changing this variable to, I'm just doing this interchange operation. And the interchange operation, out of the variable eta x, I get the variable eta x minus 1.
Yeah.
So you just have to...
No, I understand, but I thought that this superscript was supposed to be the occupancy after the jump.
Yeah, that's what is sitting here. So after the jump, you know, the occupation eta x has, you know, as a function, the occupation has become eta x minus 1. Well, you have to think about it a little bit, but I know the notation is a little bit short, but I think eventually, you know, it's much easy. It's sort of just easy to work with this notation, right?
Okay, it was the occupation there that became.
That's right.
Yeah.
Yeah.
Okay. Yeah, I understand.
Superscript j plus 1 is the configuration which would have appeared if j plus 1 had interchanged.
That's right. Yeah, that's right. That's exactly right. Yeah. Okay, so let's see. So where are we? Okay, so what I emphasized is that you know, now I took some average, and then this average, I mean, this is still a correct identity for any average I'm taking, right? Okay, so now I want to do the slow variation. Of course, you see, I mean, this is sort of, I mean, it's okay, it's a nice equation, but I cannot do anything with it because, you know, this average, I mean, here, that's the actual physical quantity which I'm interested in, which is the average occupation at the point x at time t. But this current, you know, of course, you know, I mean, it's just this function and the wave sense. So about this average, I essentially don't know anything. Okay, so now comes the hydrodynamic thing. So now we do the slow variation. Okay, and so I'm now assuming that initially I put a state which which is of a very specific form. I mean, so, you know, I have many lattice sites over here, and then I have a density profile which sort of evolves very slowly on the scale of the lattice. And if you want to sort of put a formula, then I put e to the minus beta h of eta. I mean, that of course stays, but now for the next, I take a summation over J. But now, you know, this chemical potential will be varying in space, and the sum is, so this is what I'm plotting. I mean, you know, this the chemical potential I have to convert to the density, but nevertheless, I mean, and it's this function which has a very slow variation, right? I mean, so over very large spans, I can sort of see that this is sort of essentially constant, But if I go sufficiently far, then actually I see some variation. Okay, so that's the small parameter. I have to do small variation. Okay, and now comes sort of the big point, namely that let me think of this as a function, this carbon function x plus 1, and then let me just, I can always do that. Here I was thinking in terms of putting it on an observer, but now for this next argument, it's better to think that the whole distribution has changed, and so I'm looking now at the distribution at time t, given some slowly varying initial data. Okay, and so now the step is that you claim, that's of course an approximate identity, but this is sort of it's this identity which is sort of is the central approximation within a hydrodynamic picture. So I'm just trying to say that this quantity, this complicated average over here, you see, I'm trying to say that even after a long time, the state will still have maintained this slow variation. But of course, the function which defines this slow variation will have changed. And so, so let me maybe write first something else here. So the eta of x at time t, this by definition will be, if I go on the large scale. Okay, so this is sort of the lattice scale, and the large scale. In my notes, I always, since x is used already, I use q. For as positional variables. This will be some rho q of t, right? So the way you should read it is that, if I make, a very fine lattice in terms of the x is sort of counting here. Let's see. Now I switched between x and j, and let me just see what I did. Okay. So maybe Now I keep x always here for the microscopic variables. Here I put so let me keep here the x. So x is, so to speak, the microscopic thing, which is sort of on a very small scale, and q is sort of the large scale variation, right? So the q and the x are linked, of course, but I don't really put it in my notation explicitly. So what I'm trying to say is that at a very large time, the density will have evolved, but it will be still slowly varying. So this picture will be true even after a very long time. Now, if this is actually true, then you see this is an expectation over an observable which lives just at x and x plus 1, so it will be a very local observable. And so, if it's really true that at that late time, I still see sort of approximately one of these equilibrium states with a properly modified chemical potential, then of course, I can replace this average by the average over x plus 1. But now, in the state, which is identified by this particular local density, right? This is now a fixed q here, but it's the same q which appears over here. But if this is correct, this state is now a state which has a completely constant chemical potential. Then in the next step, this can be written as simply the carbon from 0 to 1 in the Gibbs state, or in this thermal state, with a given density, and it's only this average which I have to compute. And then, of course, later on, I have to remember that if I do the hydrodynamic equation, that this has to be true at the space-time point qt. Okay, so it's this step which is sort of the essential thing. Okay? All right. So of course, at that stage is an assumption. In some models, you can maybe go more deeply, but in many models, if you think about fluids, it's this step which is really the important thing. And of course, it was a triumph of statistical mechanics that Euler just wrote down his equations sort of phenomenologically. He looked at fluids. Of course, he could study fluids, and then he sort of figured out what the fluid dynamic equation should be with a very good physical intuition. But later on, you know, people realized that if you do statistical mechanics, you can just really reproduce Euler equations. But, you know, the step in between was always a step of this type. And, you know, to actually justify, you know, in most models, it sort of is extremely difficult. But, you know, it still works as a guiding principle. Okay, so so what do we have to do now? Well, I mean, now we have to figure out what is this current. So now it's an average with respect to thermal states. So this is rho, right? I mean, so rho and mu are sort of in one-to-one correspondence, and now I have to compute this average. And what is the answer? Well, the answer is that this average is simply equal to 0. Okay? So this means that since I have a detailed balance system, you know, just doing this average will be not enough. All right. So I thought it might be still instructive, you know, to understand why this average is exactly equal to 0. So let me just go through this computation a little bit. So, you know, I do the sum over eta. I have e to the minus beta h of eta. And then I have here the sum over x, well, with the chemical potential eta of x. Okay, so let me just put here mu n. And then I have to do this computation as x 0,1, let's say, of eta. And then it's eta, this is 1. And then there's a normalizing partition function, which we really don't need. Okay, and so now how do you can see this is 0? Well, I mean, first I use detailed balance. I mean, so I know that this is the same as e to the minus beta h. Let's see. So I'm just interchanging. I mean, I do it for the bond 0, 1. I mean, so now I lose detailed balance, and now I interchange 0 and 1. Now, if I interchange 0 and 1, I mean, this term, of course, will stay, right? I mean, this doesn't know about it. So this will stay. So this is plus mu of n. But if I start interchanging detailed balance, you know, detailed balance means that I, of course, I have also to interchange the weight. I mean, so here I have a C01, and here I have the eta 01. But this, of course, is staying, right? I mean, it's you know, the detailed balance relation is saying that this quantity and this quantity are the same. Okay, now I just relabel my eta by, you know, what I call here eta 01 is my eta. So I sum, if you want so, e to the minus beta of h of eta plus mu n. I mean, that, of course, stays. I mean, there's nothing which has happened. Now, if I do the V-sum out of eta 01, it becomes sort of the original eta. So this is C01 of eta. But now, of course, I have to interchange this one. Okay, so this becomes now eta 1 minus eta 0. Okay, now you compare the two things. I mean, so it's this one. So here I have an equality, and here I have another equality. You know, this one is it's negative, and therefore it has to be equal to 0. So I just want to emphasize that the fact that, you know, in equilibrium, what physically sort of looks very reasonable, and in particular in the models we are studying, it so happens that the carbons are always equal to 0. Okay, so this means that our first order hydrodynamic equation is sort of a little bit of a disappointment, right? I mean, it's just saying that, you know, on the time scale which we are operating, I mean, nothing is changing. I mean, you know, the carbons are 0, and then, of course, the density doesn't change in time. So it just means that we're looking at sufficiently, you know, sort of, if you want, so we made an approximation which is true for very short times where the density profile doesn't change. But, you know, now we should go next and should sort of ask about what is the next order correction. And of course, I mean, we know what the next order correction should be. But now I want to sort of explain this in a slightly more detail, because, you know, now we go a step which sort of a little bit what initially you might not expect, but which turns out to be sort of the good strategy. And so since this is an important point, I mean, I put a new chapter here, which is 5.2. I call it the Green-Kubo formula because, I mean, this is what is used in hydrodynamics, so statistical mechanics of fluids, and since we are in some sense sort of in a similar context, I want to show you this one also, right? Okay. Okay, so well, I mean, now you should say, okay, I mean, we know that, this current is simply zero, then maybe we just look at the next order correction, and of course, the next order correction would say, well, okay, presumably there's some gradients, and therefore we say that this is some diffusivity which depends on rho, and then the next order correction will be sort of an expansion in the local gradients. I mean, so rather, when you think about the picture which I had originally, I was saying that on the scale which we are looking at, I mean, the density looks perfectly homogeneous and flat. I mean, in actual fact, I mean, it's a little bit tilted, and I have sort of like a small gradient here. And of course, once I induce a gradient, then physically it's quite obvious that I must induce a current. And this is now a purely macroscopic argument. And the relation between two things is given by some material constant, which is this diffusion constant, which I still have to figure out. Okay? And so you see that, I mean, if I simply assume this naively, then you will get a nice equation. I mean, now the ddt of rho is equal to, well, we had already one derivative which was coming from this formula, and now in the continuum it just becomes sort of an ordinary derivative, and we have two minus sign, and one minus sign is because, I mean, this is how we write the conservation, but this is how we write the response. I mean, so I get a dq here, and then I get a d of rho, and then I get a dq of rho, right? And so our hydrodynamic equation in this context is sort of, for the fluids. I mean, of course, you have all the carbon terms, but they are now all zero, and what is left over, the Euler equations are sort of actually, so the usual Euler equations are actually zero, and what is left over is sort of, the Navier-Stokes correction. I mean, so this is sort of, for fluid, I mean, this would be the Navier-Stokes correction. So it's a nonlinear diffusion equation. Okay, but now you see, we want to make sure that we actually have the right coefficient. After all, we want to really make predictions on the system, and if I just take, the wrong diffusion coefficient, I mean, then the predictions will be empty. So we have to figure out what is the d of rho. Now, of course, you could try to say, okay, let's impose this, and let's think. This can be done. I mean, this is fine, but it's always sort of a little bit tricky, and maybe you don't really exactly see what's going on, and at the end of the day, you might be sort of a little bit unsure whether you actually computed the correct d of rho. And so I want to show you, all these things that sort of reappear in other areas of condensed matter physics and sort of, physics of fluids. But I just want to show you how these arguments, within our simple lattice models, I mean, sort of how nicely they also work out. And so now I'm going to use a different sort of technique. Namely, I want to use, the technique of sum rules. You see, so sum rules just means that particular significant quantities, I mean, you can sort of re-express in other quantities which are sort of more accessible. And so here is the sum rule which works. And before doing this, I just want to do a simple example, actually. So let me first do an example so that you can see how these things work out. And this is the symmetric simple exclusion process, which is sort of the simplest ways which you could imagine. I mean, so, if I have here my exchange, I just do the exchange, which of course has the constraint rule, but otherwise it doesn't depend on the neighbor at all, right? I mean, so that's sort of the simplest model which we can do. I mean, in general, of course, these weights depend on the local environment. But I mean, if I want to have sort of the most simplest case, I just simply assume that that depends. And therefore, what would be the exchange rate in this case? Well, it's just saying that to have an exchange, I must have either a particle sitting here, then I can do this exchange, or there must be a particle sitting over here. So this is just nothing else but eta x minus eta x plus 1. And since it's positive, I mean, I take the square here, right? I mean, so this function is different from 0 only if either one of them is 1 and the other one is 0. Okay, and now let's see. Now let's compute the current. Okay, so that's not such a difficult exercise. I have just to take this one and I have to multiply it. Where was my current sitting? Somewhere over here, erased. Okay, so no, here's the current function. I just have to multiply it with eta x plus 1. Okay, so that you can do, and what you find is that it's simply eta x plus 1 minus eta x. So you see, in this case, the current is itself already a difference of two things. You see, that's sort of, again, like a discrete derivative. I have the occupation at side x minus the occupation at side x plus 1 and minus the occupation at side x. And so here we are in this lucky situation that, if I do this computation, I see already the difference appearing. And then, of course, this x, the derivative, which I have to do, I mean, the derivative up here, sort of appears already directly microscopically. So there's nothing to do, and what I conclude is that in this particular case, I mean, the d of rho happens to be equal to a constant, right? It's just equal to 1, because there's one derivative here, and the other derivative you have from the conservation law. Okay? But you will see in a moment, I mean, that this is sort of accidental, and in some sense comes from, the very simple exchange rate for the which we have chosen for this model. I mean, as soon as I start making sort of slightly more realistic exchange rate, I mean, then I will get a non-trivial dependence on the density. Okay, and so now in order to figure out what we have to do, I mean, this is the Green-Kubo formula. And so the idea behind this formula is rather simple. I mean, what you want to say is that so you want to start out in one of the steady states. I mean, so now I fix the density, and I take my equilibrium measure. I take e to the minus beta h, and now I have e to the mu n, and mu is sort of independent of where I am. Right? So I have a perfectly nice equilibrium state. And then what I want to say is that, so here I make sort of like a picture. I mean, so I have maybe sort of, uniform density. This is would be my Q space, and I have many sides here. And now I just want to say, okay, let's so this is the density. Now let's simply make a little perturbation at that point, and let's see how this perturbation will propagate. Now, the way how I do the perturbation is that I take this state and then so I take this state and then I simply multiply it with eta 0. You see, this means that whenever I do averages, so putting the eta 0 means that I'm now looking at this equilibrium state, but I'm looking only at those configurations where there's a particle at time t equals 0 at the origin. So that's a very simple perturbation. And now I'm asking myself, how would this propagation, this object, sort of propagate in time? And I want to simply record the density at some late time. And so you see that the thing which I'm looking at is, sort of this two-point function, eta x at time t. I mean, this is recording the density at space point x at time t, giving that at time t equals 0. I mean, if I leave out the time argument, it means time t equals 0, and then I'm doing average. The average is now, of course, over my stochastic dynamics and with respect to the equilibrium measure here, right? So this is what is called a space-time correlator. Well, if you believe in this description, I mean, then you see what you would say is that this space-time correlator essentially, must evolve according to the linear Weist equation, because I'm having a homogeneous system with a very, very small perturbation. So if I start linear Weising this equation around this perturbation, then you should see this coefficient, right? And so what you would say is that this quantity. So actually, I've given. Let's see. Do I need this actually? Yeah. Okay. Anyway, so I haven't giving a name. I mean, that's this correlator. I mean, it's just a function which depends on space, and then I mean, if I go very far out, of course, I will just see the density, and so maybe I just subtract this, and so maybe I should put here the density here, and maybe I want to subtract. I mean, so that this function, for fixed t, when I go for very large x, it actually goes to 0. Okay? Well, and then you would say that in good approximation, the x of t should be the solution of a diffusion equation. So there's first a normalization here because, okay, so I'll come back to this one in a second, but there's a normalization, and then I put here the square root of 4 pi dt. I mean, d is here, of course, the d at that given density, right? I mean, I'm doing the experiment at fixed density low. Okay, so this is this number here. And then of course, you have the ordinary diffusion kernel minus 1 over 4 dt times, now I have here x as my parameter, so that's x squared, right? And now what is this parameter? Well, I have to sort of worry a little bit about normalization. So if I start integrating, let's say, or summing over all x, I mean, then this is written already in a normalized form. And so, so if I do the sum over s of x of t, I mean, this, according to my notation, this should be equal to this number chi. And so let's go back to this concrete thing. I mean, so you see, if I start summing this over x, then I have here sum over x. But remember that, this is, I mean, this is just the particle number, so it's not changing in time. So I can erase actually the t dependence, and the rest simply stays. And so what I know from my microscopic thing is that the sum over all x of x of t is nothing else but the sum over all x of now the same expression, but now at time t equals 0 in the equilibrium state with density rho minus rho squared. You see, that's already one of the sum rules that, despite the fact that I don't know very much about the function, if I just look at its normalization, then because of the conservation law, I can actually figure out what it is. And this, of course, you see, is sort of a second derivative of a free energy, and this is what is usually called the susceptibility, and this is denoted by this symbol psi. So this appears here as a normalization, and the rest, of course, is the dynamical factor which comes from the linear Weist equation. Okay, so this is what you expect. And yes, question? You mean this one? Well, I mean, what I'm trying to say is that if I look at this experiment, then and if I look at my microscopic equation, then I would expect that this little perturbation spreads out diffusively. Right? I mean that's sort of the idea. Okay. So I have a perturbation, and initially it sort of peaked, and then if I look later, it will be sort of spread out diffusively. But then you might ask, why diffusively? Why not something else? So what I'm trying to say is that if I now sort of assume that this kind of description is correct, and if I put in here initial data which look like a small perturbation of the homogeneous system, then I have to solve this equation, but not as a nonlinear equation, but linearized relative to the uniform background. And that's just what this that's the linearized, that's the solution of the linearized equation. No? Okay. All right. So let me, all what I'm saying is that if I want to identify this coefficient, one way to do it, I mean, this method of sum rules, is to say that, you know, when I look at this equation linear-wise, then I get an expression which I can directly relate to the microscopic model. All right, so let's see how this goes. And so now, where am I? Okay, so now I have the normalization. Okay, but now we have to sort of get this coefficient d. Well, I mean, how do I compute the coefficient d? Well, it's just the second moment of this thing, right? Because, you know, when I do the second moment, and then when you do the integral, then you see it's simply proportional to dt, okay? So now we have, so now I look at 1 over, I guess there's a factor of 2 here. Let's see, what do I want to do? Yeah, maybe I don't have to write this out. Okay, so maybe I should okay, I should try to make it sort of a little bit shorter. I mean, so okay, I look at the x squared, and then I want to look at the s of x of t, right? And you know, I want to somehow normalize this. Now I've written. Okay. 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 So then there will be a normalization, which, if I write it like this, will be actually 2. Okay. So I have here a factor 2 in my notes, and sort of I'm not completely sure where it came from. Anyway, it's not very important. I mean, all what I want to say is that sort of I want to take out this normalization on this side here. Okay. And so this should be proportional for large t. This should be proportional to dt. Okay. Okay. So but now you know, I mean, I have to sort of do something with this thing. And now, of course, you use the conservation law. So the point is that maybe I have to go over here. So remember that you know, I wrote down for you this conservation law, and now I simply plug it into the formula. I mean, so in fact, I will use the conservation law in the way when I look at the conservation of eta t x minus eta the same quantity at time okay, so I want to look at eta x at time t minus the same quantity eta x at time 0, right? And this I can write as a difference of current. I mean, so this is the current from x minus 1 to x over the full time interval. So I didn't look at it, you know, the empirical current over this interval 0 up to t. And then I have to subtract from this the current from x to x plus 1, and again over this whole time interval 0 t. And so you see, if I plug this into my definition here, then of course, you know, I've written differences, and this is sort of where this factor of 2 comes from. Then what I will get is basically sort of a double integral over. You know, I have to square this because I'm looking here at the covariance, so I will get sort of a double integral, and what is appearing is the current. So, excuse me? This is the empirical. At the moment, this is the empirical current, right? I mean, so this is just counting how many particles are coming in and how many particles are going away.
But there are different, given eta x0, there are different time evolutions possible to take me to t. Should I not average over those trajectories?
No, not yet. You know, at the moment, I'm just saying, you know, this is, you know, I mean, this can take only, you know, a few values. I mean, it's either 0 or 1, but I'm saying this difference can be written as a difference of these empirical currents, right? I mean, I'm just counting how many particles are come into that side and how many particles are going out of that side. There's no average yet, okay? But you see, the average comes at the moment when I now insert this expression. So you know, basically what I'm saying is that you know, I have this eta minus eta, but, you know, I want to square this in average, right? Because, you know, this is what I have to do if I want to get the covariance. And then, you know, so I do the square here. So, you know, I just work out the square. And so here I also work out the square. And now, after I've done the square, then now I average everything. This is what I want to do. Okay? And so once I have done this average, I mean, then you see that I get a double integral from 0 up to t. Okay, I get another integral from 0 up to t. And but now okay, so wait a second. So let's be a little bit more slowly. Okay, so this is fine. Okay, so now you see that what appears here is already a difference, right? It's a difference of currents. But you see, what I really compute is the second moment over here. Where did I put the second moment? It's disappeared from my board. So I wanted to look at this quantity, but here it is. Okay, you see, I want to look at this quantity and look at the second moment. But you see, I have now two derivatives. I mean, both of them because I take the square. And so when I do these two derivatives, this is where the factor 2, I put the factor 2 in here. Then the x squared, you know, if I differentiate twice, I mean, this gives you 2 and cancels with this one. And so you see that I get now an expression which only involves, you know, the current by themselves. And so what I find is that the dt asymptotically is equal to the double integral from 0 up to t ds, the double integral from 0 up to t ds prime, and then I had still this factor 1 over 2 chi. So let me just sort of keep this here. Maybe one goes out, so we'll see. It's sort of not very important here. But now you see I have the derivative, and so but I have to do still the sum. So I still have a sum over all x. Okay, so maybe I just write this like this. Okay, so I have the sum over all x, and then I have here the average current x plus 1 of ds, and then I have the average current of x plus 1 of no, sorry. Okay, so going too fast here. Let's see what I do. Okay, so you have to be careful. I mean, so you see, one is the eta x of t, but you know, I have the eta 0. So you know, I have to insert this formula. I have to actually what I've written down here is maybe a little bit confusing. I mean, so I have to insert this formula for eta x, and I have to insert the same formula for the eta 0. And then what I then find is the following expression. Okay, so this step sort of goes a little bit too fast, but as I sort of just didn't write it out in complete detail here. But what you find is that first of all there's a double integral from 0 up to t ds prime. But then you see I will have to do this sum here. Okay, so I have a double sum over here, but this reduces to a single sum because I can use the translation invariance. And so, so this step I haven't really written out in my notes. I mean, so maybe I should have done that, ds, and then you get the current at the point 0, 1 of ds prime. And then I get here the average, and this goes now over the equilibrium state with density rho. So you see, so one sum goes out when I mean one sum comes from here, and this goes sort of, I can use translation invariance, and this one spatial sum sort of stays. So what we have written here is sort of what is called the total current correlation. Okay, it's a little bit brief, but if I write it out, I mean, then maybe sort of. Yeah, I mean, you can look it up. I mean, how the complete argument goes. Okay. Okay. So now the question, of course, is that we have sort of an expression which still looks complicated, because what I have to do is in equilibrium I have to compute this carbon-carbon correlation, and that's actually sort of an exercise which is not so totally simple, but it can be done, and let me sort of just give you sort of what comes out of these computations. It's a little bit surprising, because you have to carefully distinguish between sums which are of sort of where x is equal to 0, so that this is sort of a self-correlation between chums and chums which are sort of happening at different sites, and so this computation takes more time, and I simply cannot do it here on the blackboard, but nevertheless I sort of want to communicate to you what the result is. And the result is the following: that if I look now, okay, so let me just write it again. I mean, otherwise it will become too messy. I mean, so I look at the total carbon-carbon correlation, and here I have this thing as function of well, let me still call it ds, and then I have function at 0, 1. And let me call it ds prime. Okay, and now you get one contribution, which is the self-correlator. I mean, so if x is equal to 0 in this sum, then let me see. Actually, I want to. Sorry, I mean here. Okay, yeah, no, that's fine. Okay, so there's one contribution where this is equal, where x is equal to 0, and then there is the remainder, and the total expression looks like this. So first of all, you get simply the average jump rate from 0 to 1 times delta of s minus s prime. This is, so to speak, the self-contribution, right? I mean, and then with a negative sign, you get a minus, and then you get sort of something which you might have guessed before. I mean, it's a summation over all x. I mean, this is the summation which is sitting over here. And then you basically do this jump by itself, and the other one jump also by itself. But that's is sort of simply, the average carbon which we had out, is a carbon function which we considered before. And so, this is then the average over the carbon function, so that's x plus 1. And now I have e to e. Of course, the dynamics has to enter in some way, and so this is now the transition probability between s and s prime. And then here I have the current between 0 and 1. And so these are now the current functions. So this is a function. I have to operate with the transition probability, and that's sort of, again, a function. And then I have to average this over identity. Okay. So now you see that I have here the double integral, but this because it's stationary depends only on the time differences. Therefore, one integral goes out. So this t sort of goes out, and what is left over is the formula that my diffusion constant d of O is equal to, now I had here, still this factor 1 over 2 chi, so let me just keep this. And this double integral goes out, and what I have to do is I have to, okay, so I have to do a time integral. Well, okay, so maybe sorry, I'm just sort of want to do this. Yeah, okay. So now let me. Sorry, I mean this is maybe going too quick. So let me just sort of write it in a separate equation. Otherwise, you cannot see. Okay, so let's forget about this for a moment, right? I mean, so this was this carbon current. Okay, now I have two terms. I mean, one is the delta function, and I want to have the term proportional to t, and so I get the Green-Kubo formula for the d, so the d of rho. So there are two terms actually. So the first term is so there's 1 over the 2 chi. Okay, so the first term is very simple because. I just have to do the integral over the delta function, and the summation over x also has disappeared. And so I get just sort of a very intuitive answer, namely, it's just the average jump rate in the equilibrium state rho. That's typically, easy to compute. And this is sort of what you would have guessed naively. You see, if I think of a, simple van den Bock, and you ask yourself, what is the diffusivity? Of course, it's proportional to the jump rate, right? If I jump more often, then I will get a larger diffusion coefficient. So this is sort of maybe the naive object which you might have guessed, but since we are looking at the many particle problem, there will be some more intrinsic contribution from sort of delay and memory terms, and this is sort of the second one, and I've written it as minus. Okay, there's a minus sign over here, which, at the time when this was found, was sort of a lot of confusion whether there's the minus sign or not, but there is the minus sign, -2, and then you get the integral from 0 up to infinity dt. And the quantity which you have to now average is that you have to do the sum over all x, and you have to do the carbon-carbon function, and then you have to do the e to the lt, and you have to do this 0, 1. And this whole thing is the Green-Kubo formula. Okay, so now you still might wonder, what does this function look like? And of course, one doesn't really know very much sort of in generality about this function, but at least, from this expression, you can sort of deduce one simple property. If I start plotting this okay, so here I want to plot time, and here I plot the total carbon-carbon correlation, right? So this is what I'm plotting is this object which is sort of sitting, so to speak, under the time integral, right? And so what we noticed already, that's the first term here, is that because it's sort of this jump dynamics, for a particle system this could not happen, but you have sort of like a delta function at time t equals 0. Right? That's this part over here. Okay. And then you have a negative part, but these things is sort of a sum of exponentials, because it's basically the same function to the right and to the left. And we know that this object is with the proper weighting, which is sitting over here, has only real eigenvalues. And so therefore, what the second contribution is, that you will get a reducing part, a negative part, which goes like this. And of course, it has to be symmetric to the other side. So this is what this carbon-carbon correlation function typically looks like. And it's sort of, one of the things which I advertise for for quite some time, but nobody is so much interested in this problem. I mean, that simply happens, and you know, maybe it's not such a terribly interesting question. I always wondered, you know, sort of naively, I mean, you expect that these functions sort of should decay exponentially, but no numerical evidence. In some cases, of course, you can do a computation, and it actually does converge numerically, but there's no general argument that you know, if I have sort of a general system that this function should have a fast decay. Anyway, I mean, this is sort of the picture, and so you see that it's sort of like usually in this many-body problems, if you want to actually really compute this diffusion coefficient, you know, it's a somewhat complicated microscopic computation which we have to do. And in particular, this second term is, you know, I mean, unless you do really numerical stuff, I mean, you cannot really access. Whereas this one is sort of actually quite simple. Okay, so so let me just tell you how this works out in the case when I do the symmetric simple exclusion process. So when I do the SEP. Okay, so we know what this weights is. I mean, you know, sort of the average value of 0, 1 is simply eta 0 minus eta 1 squared. Just only exchanges, and the average is just sort of you know independent eta 0 and eta 1 with average value rho. And so you see that this so if you square it out, you find that it's 2 rho times 1 minus rho, right? I mean, this is sort of what you get. Okay. So the minus comes from the product, from the cross term, and the rho comes because eta naught squared is equal to eta naught, and therefore you find this expression. Okay. So you see, this means that. I mean, this contribution does depend on rho, but now let's look at the susceptibility, which is summation over x of eta 0, eta 1 minus rho, minus rho squared. Now, of course, it's again independent. I mean, so you know, if x is different from 0, this is rho squared, so this will be just 0. And if x is equal to 0, then this is rho, and so this is rho times 1 minus rho. And then if you compute the ratio, then you find that t is equal to 1. Okay. And so this is why I said, I mean, it's sort of, you know, a little bit accidental because, you know, this microscopically, this diffusivity sort of comes out as a ratio of a completely static quantity and about this sort of more dynamical quantity. And, you know, for the simple exclusion, it so happens that they cancel exactly and the diffusion coefficient is independent of the density. Okay, so I have to. Excuse me? Where are you looking? I mean, so I'm looking at this. This, you know, because it's a difference. I mean, this term actually cancels exactly out. You see, I mean, for the symmetric simple exclusion, you know, this object, I mean, the current function is simply eta x minus eta x plus 1, right? And if I do the sum over x, I mean, then it just cancels. That's the point because, you know, I mean, the simplification of the SEP and a few other models is that when you look at this current function, it is already a difference. And then, of course, this term completely disappears. But if I take a more general model, I mean, then, you know, it's simply, you know, this term will have to be taken into account. All right, so okay, sorry, I mean, this was maybe, I want to do this maybe a little bit more clearly, but then you have all the sums and there's limited place and, you know, limited space on the blackboard, and anyway, so I hope that at least sort of you got the rough feeling for this argument. And so now there is one other thing which I wanted to do, but I think I will do this actually sort of extremely shortly because, you know, there are more interesting things to say, and I'm not going to use it. I just wanted to point out one small thing which I think is sort of a general insight which is important. And so next chapter will be reduced to 2 lines actually. Okay, so this is 5.3, the Einstein relation. Okay, so the point is that you can also compute what is the response of your current to a driving field. This gives you the conductivity, right? I mean, so there's the conductivity, and I should have explained this more carefully, but I mean, this is sort of I want to say. So sigma is sort of the conductivity. So sigma tells you that if I apply a small force, I mean, what is the current which I induce, right? I mean, it's just like what you learn in basic physics. And then there's this Einstein relation, which tells you that this conductivity sigma is equal to the susceptibility times the diffusion coefficient. This is the Einstein relation. And when you look at your formula, then we had the d was given by this integral divided by 1 over chi, and so you see that the sigma is just equal to the time integral dt over the current. And if you do this, I mean, this was a planning, but I just want to say other things. When you do carefully this sort of linear response argument, I mean, then you indeed cover, we cover, the same formula which we had before for this current correlation, and you also recover, the relation between, and therefore you get the relationship between the conductivity, that's the sigma, and the diffusivity, which is related to the susceptibility. And I put this because, I mean, this is, independent of the particle system which I'm looking at. This is sort of a very general way of I mean, it appears, in many systems, and therefore it's sort of rather general relation. But the second thing which I want to say is that there's the Onsager form, which I think is also very useful, which again is sort of, appears in many systems, and therefore, I might point out that, of course, in our case, I mean, this is also satisfied. And so, the Onsager form is that basically writing this nonlinear diffusion equation in a somewhat different way. I mean, so I wrote it like this, and then there is the current, which is equal to rho, and then I said, okay, the current is nothing else but the current is nothing else but minus d times derivative of q. That was sort of the way how I started, and then we determined this coefficient on the basis of our stochastic lattice gas. Okay, now Onsager said that this way of writing things is actually not such a good idea. Well, of course you can do it, I mean, but the point is that that there's a more intuitive way of writing it, and the Onsager would write exactly the same current. I mean, there's no difference. It's just sort of different way of writing it. So he uses the Einstein relation, and he wants to say that the current which is induced is minus sigma. So sigma tells you, the relation if there is a force acting on the system, and what is the current which is induced. But now, the question is, what is the force? And the force can be written in a more intuitive way, in the sense that it's a derivative, not of the density, but of the chemical potential. I mean, the variation in the chemical potential sort of give you. Let me add the mu. I mean, so this is what he writes. I mean, so it's the chemical potential, sort of the derivative of the chemical potential gives you the force which produces the current, and the way how these two things are related is through the conductivity. Right? I mean, it's this relation which sort of appears in many cases, and it's sort of slightly more intuitive than the other way. Now you might say, you know, how these things are related. Well, that's sort of one of these sort of standard, you know, thermodynamic computations, which I don't want to go into, but I just want to say that, you know, if you take the free energy F, and you think of this as a function of mu, and then of course what you have is that, you know, when you take the first derivative of this gives you, you know, it comes down from the exponential, this gives the density, and if you take the second derivative, this gives you the susceptibility. And so, you know, if you work out these derivatives and you know these identities, I mean, then you can see that this is just equivalent, okay? All right, so this is a little bit short, but, you know, I want to sort of explain you a few other things which I find interesting in this context. And so maybe that's good enough. Okay, so let's see, what did I want to, yeah, okay, so now comes sort of, another point which okay, so now I jump ahead and I do the same thing for higher dimension, and then of course, you know, nothing is changing. I mean, you know, the formulas at the end, of course, are exactly the same. I mean, you just have, you know, you have to sum over the whole lattice, etc. So I don't have to go into that. I mean, but what I would like to discuss with you a little bit is now, of course, you know, you still have this nonlinear diffusion equation. I mean, the Q is now, you know, sort of becomes the gradient, and so. I mean, it's more or less the obvious sort of extension to higher dimension. But now I want to sort of discuss a little bit what happens if you take such a lattice gas, and how does the diffusivity actually depend on temperature. And the reason why I want to explain to you is that hydrodynamics sort of has this somewhat amazing, at least to me, amazing feature that when you write down the hydrodynamic equation, they tell you when the theory is going to fail. That's slightly unusual. You see, I mean, usually if you write down Newton's equation, I mean, then you say, oh, you know, they're always valid, right? And of course, in some cases, you know, maybe it's not a good approximation anymore. But here, it's the equation itself which tells you that you know, you have to pay attention. And so, let me just explain you this a little bit more concretely. And of course, you know, what I have in mind is sort of the usual lattice gas where the energy is sort of summation over nearest neighbors. With an attractive interaction either x, either y, and then now we are working in higher dimensions, okay? And then of course you know that there's a phase diagram when I have here the temperature, and here I have mu. I mean, so maybe it's actually mu plus 1 or something like that. I mean, you know, you have to sort of use the right coordinates, but you can also think in terms of -1 and +1, then you have sort of more clearly what is the symmetry, and so let me not bother too much about this. I mean, so here you have this line, there's a critical temperature, and here you have a first order phase transition between, you know, the two phases. I mean, the plus phase and the minus phase. Okay. All right, so that's fine. Now let's look at the diffusivity in this case, right? So here I have plotted it as a function of rho. Okay, so that's maybe rho. Okay, so here I plot the density rho, and here I want to plot the diffusivity. Okay, and now at infinite temperature, I mean, this is what we discussed already. I mean, then you find, of course, a very simple situation. I mean, then, you know, I mean, this is sort of T equal infinity, right? And the diffusivity is just a constant. It's just like in the SEP. Okay, now as you start lowering the temperature, then typically what happens is that sort of things cannot move so easily, and so you will sort of get a dip like this. Okay, so that's fine. Now you come. So here I have somewhere 1, and here I have somewhere 1/2. Okay, so now you come further down. At some point, you will hit this point T critical. Now what happens at this point? What happens at this point is that when you look at the Einstein relation, then okay. So maybe I put this again. So you can see this more easily. So I have the sigma divided by chi. So somehow the assertion is that the conductivity is something which doesn't know so much about the critical temperature, because I'm just pushing particles, and whether I do this sort of at high temperatures, of course the response might be slightly different, but the assertion is that the conductivity, in fact there's even a proof which I gave at some time, the conductivity is always strictly larger than 0. Okay, it never really, but what happens is that the susceptibility diverges. And therefore, if this diverges, then the diffusivity actually goes to 0, right? And so what's happening is that then the curve looks like this, okay, and it hits 0 exactly at 1/2. Okay, and now if you go to even lower temperatures, which you might want to do, then when you formally plug into these relationships, then you see that the diffusivity actually goes to 0. And then formally, it stays 0 if you just sort of naively apply the formulas which I told you, because it's, and anyway, so then it looks like this, okay? And so you see that now suddenly, these are the two density of the pure phases. That's the rho minus and that's the rho plus. So this is sort of the jump as I go from here to here. And so you see that hydrodynamics tells you that if I go below criticality, I'm still allowed to use the nonlinear diffusion equation if my density is, let's say, below the rho minus, or maybe above the rho plus. But in between, of course, something else is happening. And of course, I discussed already. In between, you have sort of a spinodal decomposition, and then of course you cannot use hydrodynamics anymore. So this equation tells you that here there's something drastic physically, and you have to sort of figure out what to do. Of course, you can still do hydrodynamics, when you look at the spinodal decomposition, but the objects which have a slow variation are actually, it's really the interface between the two phases. And so now you have to do hydrodynamics of interfaces. But this is not what we want to do. I just want to come to this point. And so now of course people know exactly how the susceptibility diverges at 1/2. So there are numbers, and then you can write it down. So what is then the equation which you get? Well, let's write. Okay. So here I had the rho of Q, but since we are interested, so now I want to put T equals to TC. Okay, and then in order to have somewhat simpler formulas, I basically want to what I call rho of Q. I want to say, okay, it's 1/2, and then it's some deviation from 1/2, which I call U. And then you wonder, what would be the diffusion equation which I have to write down, and then you see that this sort of decays here with a particular power law which is related to the power law by which this chi is actually diverging, and so what you get is an equation of the following type: is d dt of U is equal to, now we are in, let's say, d dimensions, then I have the Laplacian. These are these two derivatives. But now I have a power law for the diffusivity, which is vanishing with a particular power law. So then it's rho to the power m. And so m is some number larger than 0. And then, of course, in this special context, I mean, one knows exactly what these numbers are. And this is a famous equation, which is called the porous medium equation. And so, this has some funny features. I mean, in the sense that you see, if rho goes to 0, I mean, then nothing can move. Right? And so the question is, what is actually happening? I mean, so imagining that I put here my u, and here I want to sort of put a little bump. I don't know. Maybe I want to put a bump like this. I mean, some localized mass, extra mass here. Okay, so this, sorry. This would be the q in my notation, and this would be the u. So I put some extra mass here, but you see, I mean, this endpoint is not supposed to move. On the other side, there's a lot of pressure from this wing, because up here I still have a finite diffusivity. So this actually does want to move. So the question is, how do they compromise, so to speak? And that's something which is called the free boundary value problem. It's just, I just wanted to sort of let you know this terminology. In the sense that, usually when I solve the diffusion equation, which is sitting over here already, then I just do an initial value problem, right? I mean, I tell you what is the initial density, and then I'm just using the diffusion equation to solve. Now, maybe it's a nonlinear diffusion equation. Maybe I need a computer, but it's still an initial value problem. Now, the trouble here is that of course, I can write down the initial value, but then I don't really know what's happening at this point. And so, what people call a free boundary value problem is that part of your solution is also saying, so this point is, so to speak, the boundary, if you want. So if I think in higher dimensions, then you will have a sort of boundary like this, and the location of the boundary is part of your dynamical problem. So you have to write down, in a very naive sense, I mean, you have to write down a coupled equation. One part which sort of tells you what is the bulk, but then you have to figure out another equation which tells you how the boundary is moving. Okay. And the result of this analysis is that, in fact, in this case, I mean, if I take the porous medium equation like this one over here, I mean, they are exact solutions. So they're so-called Barenblatt solutions. Which sort of tell you in the radius. I mean, so of course, if it's non-radial, I mean, then one can, one doesn't have exact solution. But if it's sort of, let's say, radial, I mean, if I initially I put sort of like a boundary like a circle, and then the density is radial, so there's some sort of rotation invariant bump in the middle. Then Barenblatt sort of tells you, what is the long-time solution? Sort of will be some self-similar solution, but with a very explicit form, which are called the Barenblatt functions. Let's see.
Where did that come from? The density to the power m, I mean, where did that come from?
Well, this okay, maybe m is just a conventional thing. I mean, this m is related to the divergence of the susceptibility, right? So what I'm trying to say is that I mean, okay, so you see, so I pulled out, I mean, this is how they write it usually. I pulled out both derivatives in front of the row, right? And so then I have to do some integration, but eventually, the way how, sort of in a simple way how you write down this equation is that you have a row to some power m is some positive power, right? And so this is all what you see, I look here. I'm sorry, I mean, this is stupid. I mean, so of course it's u to the m, sorry. Okay, maybe that's what you confused you. Okay, so all what I was trying to, I'm looking at deviation from 1/2, and then for this deviation I get this particular, now maybe it's clear. I just sort of misprint. Okay?
And the m just comes from the dependence of the susceptibility?
Yeah, that's right. I mean, so if you want to sort of really describe, let's say, what happens for the stochastic lattice gas, let's say in 2 dimensions at criticality with this particular Hamiltonian, then you have to look up the table what the M would be. I think the M is something like 15 or so in this case. No, yeah, it's something like 15, right? I mean, so it actually sort of it's also actually quite flat, right? But then it depends on dimension, higher dimension, and then there's a mean field value and all these kind of things, right? I mean, so yeah, I mean the M has to come, but it's a purely static. That's sort of important message. It's a purely static quantity which appears there. You see, I mean, you might think that at criticality, there's something complicated with the dynamics going on, but the assertion is that no, because the conductivity, at criticality has a, I mean, it's not singular, and so it sort of comes into constants which I didn't display, but the real singularity comes only from the static part. Okay. Yeah. Okay. So I think this is actually a good point to stop here. I mean, so yeah. So let me just re-emphasize is that as we stay in the one-phase region. I mean, so if you for some reason your initial density is sort of below rho minus, then of course you are absolutely safe to use still the ordinary nonlinear diffusion equation the way we had, and nothing funny happens. And then in the spinodal region you have to do some other theory, and at criticality you get this free boundary value problem. Okay, so I guess that's sort of more or less precisely in time. So let me just tell you what I will do tomorrow. So now tomorrow. We will switch from the dynamics with detailed balance to the driven dynamics. And then you will see that we open up a totally different new world. However, and that's what I want to emphasize, because I've emphasized at the beginning of my lecture, this idea of the hydrodynamic limit, of course, stays. I mean, the point is that now the hydrodynamic equations are of a different structure. Rather than being second order, they are first order. And then now when you look at the sort of solution structure of this first order equation, they're very different from the one which we had over here. But the central idea of doing this sort of limit of slow variation, I mean, stays totally unchanged. Okay, so this will come tomorrow. Thank you very much.
Hello?
Yeah.
Okay. So just now there will be a group photo. We'll just all go down this thing. And there's no tutorial today because there's a institute colloquium from 4:30. So if you want, you can attend. But okay, no obligation. No, it's in astrophysics. So I mean, you are most welcome to attend it. So you can just go downstairs. The poster is there, so you can look at the poster, and if you find it interesting, you can attend. And also today there's a banquet, so at 6:30. So we'll all see you in the same place where we have dinner, basically. Yeah. So now we all go for the group photo.
Shall I start? Okay, great. All right, so before I start on today's topic, let me just share with you the preliminary results of the social network data, which Ritam has, very nicely collected. So this is day one, right, Ritam? Yeah. This is just day one, right?
Mid of day until mid of
Okay, so day one to middle of day two. And how many respondents?
39.
Okay, 39 out of.
So the list number of candidates in the top, the candidate list, it was 81, but some of them were online, so not really sure how many are there.
Okay, okay. So there are some issues with reporting the data. So if you are in any doubt as to how to report this data, please talk to Ritam. Okay, so if you're not sure, Ritam, maybe you should just show your hand who you are. Yeah, right, absolutely, yeah. So actually, I don't know whether that is already Ritam or not, because it's anonymized. I don't know. Okay, so the visualization has been done by my colleague, Dr. Shakti Menon at the Institute of Mathematical Sciences, who's a whiz in this network visualization softwares. So somebody yesterday was asking me about, how do you visualize a network? So actually, if you really want to know a bit about it, I'll put you in contact with Shakti. Shakti is like our in-house expert on how to render networks. Okay, so occasionally, if I have to talk about network visualization, I just, get Shakti to talk instead of me, because he's a way more knowledgeable about this than me. Ritam actually had told Shakti about some of these issues, which he just pointed out to me, that there were some names which were reported which are not in the school and so on. So this is after this is actually the third iteration of the graph, because initially when we put the graph there were lots of mistakes and so on. Hopefully this is correct, right? Okay. So this is the first day. First day up till middle of day two. Okay. Yeah. So for example, I think here what has happened is this person has actually not reported, but somebody else has reported a contact with this person. Okay. So, I mean, what to do? Okay.
Have you looked at the degree distribution of this?
Well, we haven't done an analysis because, as I said, that there are lots of issues with the data at the moment. So that's why Ritam tells me that there have been some confusion as to how to report acquaintances. So that's why I'm suggesting everybody to talk to Ritam if they have any confusion. And I've asked the organizers to send a reminder mail every evening so that you remember to do this, fill up this Google form every evening. I know it's a hassle, but it will be fantastic if you do. Okay. So especially we would like to have it at 3 times. Of course, day 1, then day 7, that is the weekend, and then at the end of the school. So at least 3 time points we would like. Well, you mean they are going to start hallucinating, huh?
No,
so
there might be more connections after the banquet.
I thought you had alcohol freely flowing in the banquet, and that's okay. Okay. Of course, alcohol acts as a social lubricant, so we can look at the effect of alcohol on the social network. So yeah. So some things about the thing. So it's color coded according to institution. So from here, of course, you can figure out to some extent the institutions from which individuals come. I'm pretty sure this color corresponds to Institute of Mathematical Sciences because I think there are 9 nodes, okay? But of course, you don't know who is who, okay? And the node shape refers to gender. So we also wanted to see whether there are more connections between people of the same gender and so on. So that's why we have also included the gender information. So you can see that there is a kind of a tight cluster between people of the same institution over here. Well, my only suggestion is that since presumably this is all from IMSC, can I just request you to maybe not be so insular and start talking to people in other institutions also? This is just assuming that this is my institute. But you can already see hubs emerging, right? So, but interestingly, there are more out degree, there's a big out degree compared to in degree, right? So presumably this person is reporting conversations with lots of people, but not too many people remember these conversations. Okay, so anyway, so one of the things you notice from this is the big issue with reconstructing social networks is it should be reciprocal, because presumably if I have talked to you for some amount of time, you will also remember that you had this conversation. But you can see there are lots of links which have only one-way connections, okay? And that's actually a very well-known, it's nothing unique to this particular group. It's a very well-known effect that people do not actually assign the same importance to some interaction as the other member of the conversation. So, you might think you had a very, very deep, meaningful conversation with someone, and that other person, said, who? I mean, did I meet this person? So happens, all right? So in any case, it would be interesting to see how this starts changing through the course of the workshop, the school. In particular, we would like to see whether certain interinstitutional links become more dense. Maybe after the end of this school. Yeah, sorry, there's a question.
One thing is happening, at least for me, as it is in my head, that I will have to fill up the form.
Yeah.
Returning from
Yeah. Yeah.
So I'm trying hard to remember the name. That may be happening with someone who is in the house, as he is involved in making this Google Forms or etc.
Right.
He is more interested in this work. That's why he is remembering many names.
Right. So you're saying there's a reporting bias. Yeah. Okay. That's also very true. So this. Yeah. Sorry.
In my defense, there will be many incoming notes to me, but no outgoing notes, because I thought I was supposed to fill in the data of people I know before this thing started.
Okay.
I filled none of
But
the names except mine. But many of
no. But hold on. I mean,
outgoing and zero incoming.
the list contains only names of people who are in this workshop, right?
Yeah, but I
So-
know nobody before coming. We didn't know anyone before coming. He thought he should. Day zero,
Day
then
zero.
day one. Yeah.
Day zero, he knew nothing, no one.
Okay.
He had
I thought
submitted on the
that.
first, whatever.
Okay. Okay, so these are all teething troubles, as you can see. So hopefully, by today or tomorrow, we'll iron out these issues. So after that, hopefully, we will start getting better data. Okay. So again, let me just impress upon you, the need to do this. I know it's a big investment in time. It probably takes 10 minutes of your very, very valuable time. But if you invest in it, hopefully at the end of the school we'll get some interesting results. I won't be here, but I will certainly send all the information to the organizers as well as to Ritam after doing the analysis with Shakti. And so maybe the organizers can actually show you some of the snapshots. Yeah.
One more thing, if people can put their name in the name section, whatever that is there in the participant list, that will be better for
Sorry?
Easier, so like people have put their name like first name or you can just put their own name, that is what that is in the participant list.
Oh yeah. So when you're saying who is
Like your name.
yeah. Maybe you can
Add
just
your
mention
name.
that.
Hello. Yeah. Just add the name that is in the participant list.
So no
Not
nicknames.
just first name, not capitalized and anything. That will be easier to like.
Yeah.
program.
So the name is not being used, as you can see, for the final thing, but the name is important in
For
order
constructing
to,
the
for example, get the institution and so on. Okay, so that's what the name is being used for. All right. Okay, so this will come in handy when I talk about things like assortativity and so on in the next lecture. Okay, so you'll see that people tend to not just people, I mean nodes in many other situations tend to sometimes cluster in such a way that like nodes prefer to connect to like nodes. So that's called assortativity. Of course, there are also opposite example where unlike nodes like to connect with each other, which is called disassortative. And here social networks typically tend to be assortative, and you can already see that here like nodes, in the sense that they share the same institution, are clustering together. Okay, so I will be using some of this analysis, and what we might also do is maybe at the on the 5th day or something, we can actually give the most recent adjacency matrix to the as a assignment to try out these various measures. So degree distribution, average path length, and so on, right? So people can actually do it with a network they identify with, in which they are a node. Okay. All right. So today is about models. Okay, and some of the stuff that we learned yesterday about metrics. So we will now see how those metrics work out in the context of specific models. All right. So until I would say 1998, which is not too far off, right? And just about 25 years back, pretty much the only two models of networks that people used to work with were these two classes: the regular lattice or grid, and typically this used to be studied by physicists. So like various kinds of square grid, hexagonal grid, triangular grid, and so on. And mathematicians, especially those who work on graph theory, would work on a completely different class of networks called random networks. Okay. Now, their properties are actually very, very different. So the average path length of regular lattices tend to be some power of n. Okay. So where n is the number of nodes. So so some function of n, or n to the power something. So for example, if it's a linear chain, then the average path length would increase basically linearly with n. If it's a square grid, it will typically increase as, I think, square root of n, and so on. Okay, and the clustering typically tends to be high, except for very special cases. For example, in a square lattice, the clustering is 0. So that's basically the answer to one of the assignment questions I gave yesterday. That for square lattice, that's a fairly special case where even though it's a regular lattice, so when I say regular, I mean basically regular in the sense of every node is essentially identical to every other node in terms of its neighborhood and so on. So most regular lattices tend to have high degree of clustering, excepting for the square lattice, okay, with nearest neighbor interactions. But typically, like for example, if you look at this lattice, you notice that if you consider this as your node of interest, then you can work out the clustering coefficient. Okay, so On the denominator, so how many neighbors do you have? 6, right? And what's the number of possible links between them? 6 choose 2, which is 15, right? Okay. Now, how many of these are actually mutual neighbors? So, 1, 2, 3, 4, 5, 6, right? So 6, could there be any others? No, presumably not, okay? So basically your clustering is 6 by 15. Now you might say, hold on, this is local clustering, I'm just referring to a single node. But in this particular case, in a regular lattice, this is also the global clustering, because every node is identical. Every node has exactly the same neighborhood structure. Okay, so that's why somebody was asking me that in one of the questions in my assignment I haven't mentioned the n for the lattice when I'm asked you to calculate the clustering, and that's because you don't need to know n. It could be infinite extent for all you care. Okay, because every node has exactly the same neighborhood, so you can calculate the local clustering, and that will also be the global clustering. Okay, so that's what is meant by regular lattice. All right, so typically you see that this is pretty high, 6 by 15. Okay, so that's higher than 1/3, higher than 33%, for example. Okay, the other thing is that if you look at the degree distribution, the degree distribution would tend to be completely localized around a single point. In this particular case, 6. So it's 0 everywhere else and only finite at 6. That's because every node has the degree 6, and there is no other degree, no node with degree 5, 4, 3, 2, or 7, 8, 9, right? So the degree is like this. All right. In contrast, random networks, and sometimes in the literature they would be referred to as ER networks, where ER stands for the names of two mathematicians, Erdos and Rennie, more about them later. And there you find that the average path length goes as not a polynomial function of n, but as log of n. Okay. Now we know that a log actually grows way slower than any polynomial function of n. Okay, it grows slower than root n or n to the power 1/3 and so on. Right. So this is a surprise, right? So you are increasing n, let's say by a factor of I don't know, maybe. I'm trying to find a number whose log will also be a whole number. Okay, fine. So maybe you make it, sorry?
10 base log, 10 to the power.
Okay, whatever. Make it 100 times, and then you find that the average path length only increases twice. Okay, that's incredible, right? So that essentially means that you can make it extremely large, and yet you can reach any node from any other node in just a few hops. Okay. So you might ask, why is this? So we will look into this. Okay. You can start thinking as to why it should be log n, and we will then come to the answer later on. It's a very, very simple intuitive argument as to why it should be log n. Okay. Yeah. No. So n is basically for the linear chain. It's a function of n.
For the linear chain, but for
and
square.
For in general, it would be n to the power 1 by d.
1 by d. Okay.
Yeah, correct. So that's why I said polynomial, okay, of n. Yeah, clustering tends to be low. Okay. especially if you make n go to infinity, but the degree remains finite. Okay. So then typically the clustering would actually tend to 0. Okay. Again, we will see why later on. And the degree distribution is the famous Poisson degree distribution. Okay. So it's a single parameter distribution where the parameter that characterizes the distribution is just the average degree. Okay. Again, we will see why. Okay. All right. So regular lattices are, of course, bread and butter of physicists, so I won't talk much about them. But random networks may not be familiar to most of you, so let me just delve a little deeper into random networks. So these networks are constructed by essentially placing links between pairs of nodes with independent identical probability P. Okay, so probably the first people to study this in mathematical sense were the famous computer scientists Solomonoff and the game theorist Rappaport. So Solomonoff is of course famous as the founder of algorithmic information theory, and Rappaport is famous for his work on prisoner's dilemma, games, and so on. So both are very famous for their other work. So usually what happens is that if you are already very famous for some work, then even if you do the first paper on some subject, people forget all about it, right? Because it's like just one out of your enormous output, and you're more famous for other works. Okay, so typically, although random networks were first studied by these people, we don't talk about them as SR networks, which we probably should have, Solomonoff-Rappaport networks. But instead, so in fact, if you look at their paper, this one, which was published in Bulletin of Mathematical Biophysics in 1951, you can see that, you can see that they are actually deriving many of the results which later Erdos and Rennie would actually go on to derive again, all right? But this paper somehow basically just went under the radar, just completely sank without a trace. Okay, so we know random networks primarily as under the names of these two people. The famous Paul Erdos, I think this is one mathematician whose name, almost any average Joe who has some, interest in reading books will know, because there's this very famous biography of him called "My Brain is Always Open," and so it's sometimes said that Erdos has collaborated with the most number of people. So in many circles, people talk about their Erdos number. So if you have a paper with Erdos, that means your Erdos number is 1. If you have a paper with someone who has collaborated with Erdos, your Erdos number is 2, and so on. Okay, and how many people are familiar with Erdos number? Okay, so if you are curious about what is your Erdos number, there's actually a website where you can go and try to trace it. So you can try to see how you can connect with someone who is connected with someone who is connected with someone who finally goes to Erdos. Okay, I think my Erdos number is probably let me see, 4 or something, because my postdoc advisor at Cornell, his advisor had worked with Erdos's collaborator. So basically, there's a quick chain. Okay, so right. So, and Alfred Rennie, although not as well known as Erdos, was of course an equally famous mathematician whose primary work was on information theory. So in, just about 8 years after the Solomonoff-Rappaport paper, they wrote their first paper and then followed it up with a series of papers in which they basically worked out the mathematical framework for random networks, and we primarily know these random networks in their names because of this. So they didn't just do this one-off paper like Solomonov and Rappaport and then just go off to do something else, but kept basically publishing more detailed aspects. And then later their student Bela Bolobash followed this up. So usually, like if you want to learn about random graphs from a maths point of view, the Bible is Bela Bolobash's random graphs. Okay, so I had the fortune or misfortune of once attending a course of lectures by Bela Bolobash in ICTP. So at the end of each lecture, he was giving out assignment sheets. Like you just hand it over around and say that, okay, tomorrow I would like you to, in a very Hungarian accent, tomorrow I'd like you to, come up with the answers. So I was way younger then and, pretty enthusiastic. And so I go back to Hotel Adriatico, which is this guest house of ICTP, in my room. Start out with problem number 1. And 1.5 hours later, I'm still at problem number 1. So I was fortunate because I was sharing this room with Bolobash's PhD student, who was supposed to be one of the, helpers in the course. So he was out at that time. So, 1.5 hours later, he comes in, and then I said, I'm extremely sorry. I know I'm looking really dumb, but, somehow I just can't make head or tail out of problem 1, how to approach it. So he looks at me and says, what is your background? So I said, physics. So he nods and said, not for physicists. So yeah, I mean, the book is very forbidding one, and it requires a way of approaching graphs which is very different from way physicists are famously, very unrigorous. My math colleagues at IMSC kind of shudder sometimes the way, we kind of say that, oh, we have proved it. So what proof? This is not even a proof. I mean, this is not even a conjecture, right? So, so anyway, so if you look at their work, actually you find that they're talking about 2 different classes of random networks. Okay? And it's important to know the distinction because depending upon what problem you're trying to solve, one or other of these ensembles may be more useful. Okay? So one of these ensembles is called the GNL model, okay, or the GNL ensemble. So how is this defined? It basically says that the GNL ensemble has all networks which has n nodes and L links, and then you're choosing members of this set at random. Okay? So when you are creating a random network using this ensemble, what you're doing essentially is you just put your hand in that set and just pick up one member of that set at random. So let's give an example. So suppose you look at the G3, 2 ensemble. So 3 is the number of nodes and 2 is the number of links. So suppose you label the nodes A, B, C. So then these are the 3 possible members of this set. Okay. So when I'm saying that I am constructing a random network using the G3, 2 ensemble, it means that I've just picked one of these networks with equal probability, that is 1/3. Okay? So that's essentially what it means. All right? So this is the advantage that if you want to make sure that the number of links, so you are basically trying to study the properties of a whole ensemble of graphs. Okay? If you want to ensure that the number of links is the same for all the various network realizations, then you need to use the GNL ensemble. The problem with GNL ensemble is doing analytical stuff with GNL ensemble is quite tough. Okay. So they also defined the GNP ensemble, and this is closer to what actually Solomonov and Rappaport were doing. Okay. So the Solomonov-Rappaport model is actually the GNP model. Okay. So in GNP model, instead what you're saying is that I'm not fixing the number of links, rather I'm fixing only the number of nodes, and then for all possible pairs n choose 2, I am basically saying that a link exists or does not exist with some probability p. Okay. And you specify p. Okay. So the ensemble is specified by the probability of there being a connection between any pair of nodes. Okay. Now this of course has a problem. So this now means that you will have nodes, you will have networks having differing number of links. You may end up with having 3 isolated nodes in the ensemble. You may end up with the ensemble having all links between the nodes and anything in between. Each of them will have some probability. Okay? Of course, if p is, let's say, half, it's very, very unlikely that you're going to have 3 isolated nodes, and it's very, very unlikely that you're going to have all 3 connected. But of course, with some probability, that can also happen. Right? So if you have the ensemble G3 comma half, that means you are basically talking about all possible networks of 3 nodes such that each of these links AB, BC, AC occurs with probability half. All right. So that means you can actually work out each of these things. So you'd say that, okay, what's the probability that you'll have 3 isolated nodes? So that means there's no probability of a link between AB, which is half, times there's no probability that there's a link between BC, which is also half, and the probability that there is no link between CA, which is also half. So it's half to the power cube. So with probability 1/8, you would have this configuration. Similarly, with probability 1/8, you'll have this configuration. Okay, and then since these nodes are distinguishable, this various. So, for example, this particular thing will also occur with probability 1/8. This will occur with probability 1/8, and so on and so forth. So you can work out what is the probability of each of these configurations. Okay. Now, an interesting result that they proved was that so it's pretty clear, right, that as p becomes smaller and smaller, it becomes more and more likely that the network is going to be fragmented, that there will be some nodes or groups of nodes which you can't reach from another group of nodes. Okay? Whereas when p tends to 1, almost with certainty, you are going to be able to find a path from any node to any node. So the obvious question would be, what should be the value of p such that it's almost certain that you'll be able to find a connected path from one node to another node. Okay. So it turns out that you can actually work this out analytically. I'm not going to do the actual calculation because you can actually look this up in many places. One of the simplest ways is to assume that you just have one isolated, you are just talking about the rest of the n-1 nodes are connected, and you are saying that, okay, there is this one node, the nth node, and now you want to basically say what is the probability that no link exists from any member of this set to this node. So basically that will say that, this is disconnected, and so you ask what is the probability such that this is not going to happen, that there will be at least one link from this set to this set. So that's for just one node versus n-1, and then you try to generalize this for n prime and n-n prime. Okay. So that's how you can work it out. Anyway, so what you find is that as n tends to infinity, if p is greater than 2 log n by n, it's almost surely connected. That is, you will be able to find a path from any point to any other point. Now that looks a horrendous expression. Okay, So there are ways of thinking a little more cleanly about it. So one way to do is, you can say, okay, how can I express it in terms of number of links, L, or expected number of links, L, rather, because now the number of links is not a constant, right? Because it can vary from network to network. Any ideas how I can turn this into an expression where I'm talking about the expected number of L rather than P? Okay, well, actually, strictly speaking, it's n into n minus 1 by 2 times P, which is L. What you said is actually the average degree. Okay, so technically, NP is the average degree, which is also another interesting thing. I mean, we can also start talking about in terms of the average degree. So if you talk in terms of average degree, it basically says that if the average degree is greater than 2 log n, okay, then it's almost surely connected. Okay, or in terms of what do you call L, you're basically saying that if L is greater than, so basically, you take n over here and then you multiply both sides by n minus 1, this 2 comes over here, so it becomes n minus 1 log n. So essentially you can ignore this 1, and so it becomes, if the average number of connections is greater than n log n, then you're almost surely connected. You'll always be able to find a path from any point to any point. So that's sometimes people ask me, okay, how do I ensure that when I'm constructing a random network, it won't get fragmented? Well, that's the answer. So you make sure that your probability of connection or your expected number of links is greater than that number. So notice that if it was n squared, that means it would be a click, right? So it basically says that n times some function of n, but that need not be linear, that can actually grow much more slowly with log n. Now, an interesting point to think about here is that, can you try to relate it to something that I already mentioned? What goes as log n? The average path length of a random network. Okay, so you can start thinking, could there be relation with that? Okay, so how is it that, that the average degree has to be greater than the twice. So basically what you're saying is that the average degree has to be greater than twice the path length of that graph for it to be almost surely connected. Okay, so that's an interesting thought which you can think about. Like, you can try to think whether there'll be any connection. I mean, that's not the way that people actually rigorously prove it, but it's an intuitive way of thinking about why this log n comes about. Yeah.
It is almost surely to be connected. So is there a measure which tells you that the probability of being connected is high, or it is like it's almost surely? So is there some measure?
Yeah. So this almost surely connected is the typical way we express things when we say, how is this actually, so so what we are asking is, what is the probability that the network is not fragmented? Okay, so the probability that G is connected. Okay, so this, suppose you are measuring this as a function of small p. Okay. Now, suppose you do this for a finite n. Okay. So for a finite n, this will look like this, right? So as you make p larger or closer and closer to 1, we know that this will reach 1. Okay. So when I say almost surely going to be connected, that means I'm talking about a statement which is true only in the limit n goes to infinity. So at n, as n goes closer and closer to infinity, this becomes sharper and sharper. So typically when I say it's almost surely to be connected, this is what I'm referring to, that as n becomes larger and larger, this curve is going to get sharper and sharper, eventually reaching a step function as n goes to infinity. Okay? All right. Yeah.
So during computations, we usually use a finite size of the system.
Correct.
So how do we, I'm not sure how to incorporate that error we get due to this. Let's say assume I work with a connected system, but then in simulations I always don't get a connected system. I might not get, even if I make sure this happens to log n by n. So how do I make sure that I incorporate that error that comes because of that?
Yeah, okay, so very good question. So you're referring to the fact that how exactly does this transition region scale with n, right? So there have been actually studies which have actually tried to show, so this is very much like critical phenomena, right? Where, we know that at limit of n tending to infinity, it's going to go like this, but in any finite size simulation, we know that it goes like this. So what we can do is, we can actually measure the transition region and see how this scales with n, correct? So that's how we basically get an idea of, how broad this transition region is. So people have done similar studies for this transition also. Okay, so I don't remember offhand how the transition region scales with n, but you can look this up. Okay, so in practice, what we find is that when you are dealing with something like order of thousands of nodes, this is already pretty good. Okay, so and to be very frank, if today you are doing a study which has less than thousands of nodes, I don't think any decent journal is going to publish it. Okay, so this is pretty good enough for most calculations. Okay, all right. Now let's see. Okay, so I already mentioned this before. Largest connected component. So suppose you are looking at this GNP ensemble, and your P is not high enough such that you get a connected path from every point to every other point. So now what happens is that part of the network you'll be able to go from anywhere to anywhere, but from this red colored thing you cannot, for example, go to this one or this one, and there are also lots of isolated nodes. Okay, so we can also try characterizing this. We say that what is the size of the largest connected component of a network. Okay, so the question we are asking is that as the network becomes larger and larger, that is as n tends to infinity, how does the ratio of the size of the largest connected component to that of the network behave? So when we look at this GNP random network, for example, we find that when p equal to 0, that is the probability of forming a connection between any pair of nodes is 0, not surprisingly, the size of the largest connected component is simply 1. That's because the largest connected component is simply the node itself. It's not connected to anything else. On the other hand, when p equal to 1, that means every node is connected to every other node, and so that means the largest connected component is n. Okay? So we know that NL is going to be 1 at one end and n at the other, or rather NL by n. So we know that NL by n, this ratio, is going to be 0 because 1 by n for n large enough is effectively just 0, right? So we know that it's going to be close to 0 at this end. And we know that it's going to be 1 at this end. So this is p equal to 1. Okay. Question is, what is happening in the middle? Okay. So is it like this? Is it like this? Is it like this? Is it like this? And so on. Okay. So by now you might have actually guessed which one it would actually go like. So it turns out that it shows a very characteristic phase transition. Okay. So as you gradually increase p, we find that up to a point it remains effectively 0, right? So that means that this is the size of this largest connected component is growing, but it's not growing proportional to n. So it's growing way slower, okay? Or it remains almost a constant, right? So it's not an extensive variable. However, as it crosses a critical value of this probability, suddenly the size of the largest connected component becomes extensive. That is, it starts growing with n. And so therefore, NL by n now becomes a finite quantity, which gradually tends to 1. Okay? Now the interesting thing is, where is this happening? This is happening at a probability value 1 over n. Now 1 over n is very special, because what is 1 over n? It simply means that the average degree is what? If probability of connection is 1 over n, what's the average degree? 1, right? So that means each node on average has 1 connection, okay? And that is enough to ensure that the size of the largest connected component will become extensive, okay? Anything less than that, you're going to have small isolated fragments, all right? Yeah.
So previously we said that the average degree has to grow like log n.
Yeah.
For the graph to be connected.
Yeah.
But now you're saying that the average degree has to be 1 for the largest component to scale with
N. Yeah.
So, so these two are different.
These two are different. Why?
Yeah. So
Excellent question. Excellent question. Let me throw the question to the students. So, this is a very good question. So, what's the answer? What's the difference between these two things? Yeah. So the question is this. So in the previous slide, I mentioned a critical probability, which was that the average degree has to be greater than twice log n for the network to be connected. Okay. Now I am saying that the average degree has to be 1 or greater than 1 for the largest connected component to become extensive. Okay. What's the difference between these two statements? Yeah. So the difference is this. Absolutely right. The difference is this. In the previous case, I was insisting that all the nodes should be reachable from every other node of the network. So the largest connected component size is actually the same as the network. So NL by N is actually 1. Okay? Whereas here what I'm talking about is NL by N is greater than 0. Okay? So this is the difference. Okay? Yeah.
So the disconnected part that also scales with n once the P is greater than 1 by n. When you are looking at the largest connected component,
yes.
whatever you are leaving out, because the largest connected component is scaling with n.
Right.
Whatever is not part of it, that is also scaling with n.
Why should it scale with n? Is there an obvious argument? Why should it scale with n? Okay.
Scaling,
No, but what do you mean by size of the largest?
Whatever is remaining,
yeah.
that fraction, that part, that will
yeah.
also scale with n.
No, but that was anyway scaling with n even before, right? Even below PC. So that's not very interesting. So it does not change its behavior. Yeah, Abhishek, you had a question.
So when you calculate mean path,
Yeah.
that is for points on the cluster, I guess, right? On the connected part.
Yeah.
Because otherwise it will be infinite. So
Correct,
you just
correct.
choose.
Although as I mentioned in the last class, you can take the harmonic mean in order to take into account, like if you want to,
right,
consider also this disconnected
But
fragments.
that would be equivalent, I guess, right? Equivalent to just taking points on the connected part.
No, that's not equivalent.
Oh, is it? Okay.
So what you're doing is this. Yeah, so this is actually the same graph that we saw yesterday's assignment, right? The 10 bridges of Chennai. Okay, does anyone remember what's the average path length? 7 by 6. Yeah. So now what I'm going to do is I'm going to say that there is a disconnected fragment here. Okay. I'm going to ask, how do I measure the average path length of this system? Now, if we try to do it the way I did yesterday, of course, I will get 1 for this and 7 by 6 for this. But when I try to compute the overall path length, it will diverge. Okay. So now I want to, do it in some way such that I can still take into account the fact that they're disconnected fragments, but still get a number. Okay. So what do? I basically now start asking the question that, okay, what is the harmonic mean of the path lengths? So how is harmonic mean calculated? So 1 by HM equal to summation over 1 by di over I equal to 1 to L.
The links.
L is the number of links. Okay. So that's typically how we define the harmonic mean. Okay. So now notice that again, so what I'm going to do is, I'm going to do, so this will contribute 6 terms, right? So 1 plus 1 plus 1 plus 1 plus half. Okay, so far so good. Okay. Then term would be given by this, which is simply 1. Okay. And now I will get lots of zeros, right? So how many ones are we talking about? So we are talking about now, so here we have 4 nodes and here we have 2 nodes. Okay. So how many possible links are there? 8, correct? So there would be, a whole series of 0, 0, 0, 0, zeros, 8 of them. Okay. And then what is L now? Total number of edges. So there's 6 from this, 1 from this, and 8 between. Yeah, yeah. So 6 choose 1, 2, 3, 4, 5, 6. So 15, right? Yeah. All right. which you can also check by just calculating the fact that there are 6 possible paths, 1 possible path and 8 between them, so 8 plus 7 is 15, okay? All right, so now let's do the calculation. What do you get? So this is 5, 6 plus half, so 13 by 2, yeah. So okay, so this gives me now the harmonic mean as reciprocal of this, or 2 by 15 times 13. So so that's approximately, sorry? Yeah, I mean probably a little less than that, okay? Yeah. Okay. Now, an exercise which I leave for you is, now you just add one connection from here to here and then compute the harmonic mean, okay, and see what it gives. Okay. No, I'm not telling you to do right now, but just do it, and you will immediately see that this path would give you a shorter value, okay. So this effectively tells you that how the fact that you have disconnected fragment essentially increases this harmonic path, okay, in some sense.
It decreased it. It became really small.
Which one?
The 2 by 15 into, that's like 1/100. So you got a very small number.
Yeah. So now what
because
will,
of the disconnection.
yeah, but now what will happen is this number will become even larger because you add more
then it
values,
become, yeah.
and so the denominator would be even larger. So it will become smaller.
But then it looks like it's not giving a good representation of this 7 by 6 and 1, right? I mean,
No. So the point is, if it's disconnected, you expect that the path length would be higher than if the connection existed. That is what this is trying to capture.
but it's giving a very small number, right? It's not giving a large path.
But if you connected this, that will give an even smaller value.
Okay.
That is the point. So usually this is, if you don't take the reciprocal but just calculate this value itself, this is sometimes known as communication efficiency. Okay. So in communication efficiency, the higher the better, right? So you will find that if there is a disconnected fragment, there are all these zeros which don't contribute. So the communication efficiency will be smaller than a connection existed, where you will actually get finite contributions. So the communication efficiency, if a link had existed, would be higher than if you had disconnected fragments. So that's another way of looking at it. Okay. No, I think what you're trying to do is you're trying to connect this with this 7 by 6.
Yeah, like if I just, for this connected thing, if I calculated the mean path, does that agree with the harmonic mean formula? No, right? So the harmonic mean formula gives me something else. Then.
Okay, so you're saying that, suppose I forget about
this formula,
path,
right?
okay?
No, even if I have that link.
No. I mean, I'm saying that, suppose I'm trying to calculate only the harmonic mean of this thing.
Yeah, right, yeah.
Okay. So then what will it give me? So now it gives me, so there are 6 paths times
4C2, so
by 4C2 is 6, and so it gives me 13
6 into 13 by 2, right?
by 2.
So it's a very small number then.
Yeah, okay. Yeah, actually, sorry, I think I made a mistake. I think it should be 1 by L probably. Yeah.
1 by L.
Yeah.
That
Sorry.
makes sense, right? Yeah.
Thanks for pointing it out. I put the L in the wrong place. It's actually 1 by L. Thank you. Yeah. So sorry, folks. Apologies for the mistake. So it would be 13 by 2 into 15. So that's 13 by 30. Okay, and so therefore this would be 30 by 13. Yeah, thanks. And so now here 1/6 and 13 by 2, so this is 13 by 12, which is kind of close to the value of 7/6, right? That I talked about. Not exactly 7/6, but it's pretty close. Yeah. All right. Okay. Okay. So please, if you have made any notes, please make this correction. So the L should actually be in the denominator and not the numerator. 1 by di. Yeah. Okay, any questions? Yeah.
Regarding a question asked previously, so after you cross the critical point, thank you. Regarding a question asked previously, after you cross the critical point, the number of components which are not in the connected cluster would decrease faster than, would not increase as fast as than right? Because they will become connected to the bigger cluster
Right.
faster than, yeah.
Right.
Yeah.
So you can think of them as
I mean,
just
it's
a
not that
complement
trivial.
of this. Okay.
Yeah.
So here, for example, so if you look at the fraction which is disconnected, you just flip this graph. Okay. So basically, that will say that as your vertex degree becomes higher and higher, eventually the fraction of the disconnected part would become non-extensive, whereas this part is still extensive. Okay. So that part is right, what he mentioned, that in this region, both the fraction of the connected part and the fraction of the disconnected part is extensive.
Mm-hmm.
But where it becomes non-extensive is actually here, whereas where this was non-extensive is actually here. Okay, so that's the difference.
Okay.
One is just complement of the other.
What happens on the line, the phase transition line, the fragmented and non-fragmented connected? What actually happens at the line? Like at the line we share both the regions, fragmented and connected. So what actually happens at the line?
Brilliant question. So if you have done percolation, you know that this is exactly the percolation point where it creates a spanning. If this had been on a lattice, for example, this is precisely where a spanning cluster is formed. Okay. So there's a very nice connection between this transition and bond percolation. Okay. So in bond percolation, typically this is of course studied in a lattice. So in some sense, this result is a generalization of the bond percolation problem for an arbitrary connection topology. Okay. So where any node can have a non-equal number of neighbors. So bond percolation, which I think traditionally or whatever historically it had originally been studied for some very practical problems. So for example, in the First World War, both the sides I think employed poison gas, and so it became very important to come up with good designs of gas masks. Now, so the way that gas masks work is that you have this charcoal as a filter, and you pack it at a particular density such that air molecules can find connected path through this filter. However, poison gas molecules, which typically are bigger, will be trapped. Okay, so that's the idea. Now, how does this work? Okay, so or what is the optimal packing density such that you don't asphyxiate, it doesn't block air so that you just fall off, but at the same time it shouldn't be so loosely packed such that poison molecules can go through. Okay, so you can think of it like this: that for the poison gas molecules, it's basically trying to go through a maze. It's like one of those mazes we used to solve as a child, right? So the question is, if this is the external atmosphere and if this is inside the mask, can a gas molecule find a series of connected paths to go from this end to this end? Okay. So if you study this on a lattice, the way you do this is, you put the points on a regular square grid, and then with a particular probability P, you start picking pairs of dots and then connecting them. Okay? So for P equal to 0, nothing will be connected. For P equal to 1, all of these will be connected. And for an intermediate value of P, for example, you will find that some of these dots are connected and some not. Okay? So you're always trying to connect nearest neighbor dots, by the way. You don't have long range connections. Okay? Okay. Now the question you ask is, at a particular value of P, would you be able to find a path that starting from this end goes up to this end? Okay. So that's basically the point of this exercise. And so the question is, what is the critical value of P such that for the first time you'll be able to create a connected path from this point to this point. So that's essentially what we call a spanning cluster. Okay? So basically it starts spanning the system. Okay? So in a sense, what we talked about is a generalization of this problem. So what we would call the emergence of a spanning cluster is what is actually happening here at the network level. So basically, you find that the largest connected component becomes a finite fraction of the entire network for the first time. All right?
Sir,
Yeah.
another question is,
Yeah.
sir, as the number of n is increasing, at
Yeah.
n,
Yeah.
the LCC is also increasing. Like for the first time, if the n increases and becomes a huge size, will it be like every node be connected with each other at a huge amount of nodes at like when n is very huge?
See, it doesn't matter what is n, because here we are essentially talking about a scaled value, right? It's the fraction we are talking about. So as it's indicated, for a finite value of n, you can see that there's no sharp point at which it suddenly goes from 0 to 1. That sharp point is reached only once n diverges. Okay, so it's not like things would change drastically if you change n. Essentially what is happening is that the transition is getting sharper and sharper, just like any other phase transition. Okay. Any other question? Yeah. Yeah, so if you have this P going to 1, eventually it will take over the whole thing. In fact, it doesn't even have to go to 1. As we just saw, it just has to cross n log n, right? Yeah, you had a question.
So the largest connected component is showing this transition, but are there other quantities, say like the distribution or the variance of the size, different component sizes? Would that also show transitions like this?
Okay, very nice question.
What is order parameter?
The order parameter is this.
That's one.
Yeah.
But
yeah. So like one question you can ask is, could there be two giant components? Okay. So like could there be another, the second largest component? Would that also show extensive behavior? You can ask that question. Okay. It turns out that okay, so there are ways to show that you won't have two or more giant components, okay, once this transition is reached. Okay, the proof is a bit involved, but Bolobash's book actually has that proof. Okay, but sometimes we are interested to know what is the size distribution of these fragments. Okay. So that's actually something we worked on a long time back, and in fact it has very interesting connections with I think the transition that are seen in work. I think that Abhishek's Abhishek, did you work on Takahashi model also ever? No, not you. Okay, but his colleagues at TIFR have worked on, like Shotto has worked on it, right? So Shota Majumdar and so on. So there you see that you see a transition from an exponential distribution to a condensate via a power law. Okay. Interestingly, if you look at the distribution of these components, okay, like not just the disconnected fragments, we are looking at basically the size distribution of the entire thing. Okay. So what we find is that for very small value of p, the sizes of these components follow an exponential distribution. Okay. At the other end, we get a condensate. Okay. So basically everything gets clumped into a single large giant component with size n. In between, at this critical point, we see a power law distribution. Okay. So it kind of shares this feature with many other models in statistical mechanics, that you have a crossover from one distribution to another distribution via a power law. Okay. So the power law is actually indicative of the phase transition.
And the point is also similar, where the power law starts arising.
Yeah. So basically it will start precisely at that point. Yeah. Okay. So where were we? Okay. Yeah. Sorry. Let me hide that slide. Okay. First, let me ask you. So I said that the average path length of a random network goes as log n. Right? Anybody care to guess where I'm getting this log n from? Using a simple intuitive argument. So one thing you might need to know is that for large n, if p is small, the probability of forming loops of any order becomes very small. So you can treat a network locally as almost a tree or a Bethe lattice. Okay, that's an important point. Okay, so I suppose not everyone is familiar with Bethe lattice. I'm getting blank looks. Okay, but when I say that something is a tree, this is what I mean. So it means that there are no loops. So the Bethe lattice is a special case of a tree where the coordination number of every vertex is the same. In networks, it need not be the case. You could have different number of links coming from So this is what I mean, that locally I can treat the random network as something like this, that the probability of loop is very small. Okay. So given this, can you actually give me an argument as to why the average path length should go as log of n? So basically what I'm saying is you can treat the random network as a tree, right, of n nodes.
Binary tree, then you can reach to the lowest row by like log n hops, because you are consider like all your search space is divided by 2 at every jump from one level to the next level. So essentially the log is coming from there, I think.
Yeah, except that you need not be confined to binary, right?
Yeah.
So you can.
So for the Bethe lattice, it will be like you are hopping like when you are starting.
So you can take your coordination number to be k.
K.
Okay. In fact, even if k is not the same for all nodes, it doesn't matter. You can just take the average degree.
Yeah.
Yeah. And you can use the same argument. Yeah.
Suppose you start from the center, let's say. Then you can do a random walk kind of thing. And every step you can make, let's say, approximately 3 choices. I'm not counting going back.
Well, actually, on average, you make k choices.
Yeah, on average, whatever. I mean, for this case, let's say 3. I'm assuming Bethe lattice. So the number of paths till you reach the endpoint of the lattice
would go as 3 power size of the lattice, which goes as which is a logarithmic kind of thing, I guess.
Yep.
Yeah.
Okay, so both of them actually have got it. So let me just work out in detail what they are saying. So, this is a kind of a regular tree where every node has degree 3. Okay, so you can look at any one node and you will find that essentially there are 3 neighbors. Now, this need not be so rigid. So you can actually have something like this where different nodes have different number of branches coming out of them, such that the degree is different, but you can still define a average degree even in that case. Okay. So what I'm going to claim is that the average path length is actually going to go as log n. Actually, it's actually log n divided by log average k, but since this is a constant, we can ignore it. Because we just want to know how it scales with n. So what we are going to do is we are going to look at the GNP ensemble, and in a GNP ensemble, if p is small, then the probability that there would be a loop is just p. So basically you're asking what's the probability. If you say that there's a loop, that means you are saying, okay, with probability p, this and this are connected. And so if p is extremely small, there will be very small likelihood that there is going to be a loop in the system. Okay? Now, then we use the argument which your friends have actually just pointed out. So we start from, let's say, some vertex, and we call it 0, and we ask, okay, how many neighbors are located at a distance 1 from this? So if your average degree is k, that means at a distance 1, you have k average neighbors located at a distance 1 from you. Then you ask, okay, each of these are on average connected to, let's say, k neighbors. And then you ask, okay, what is the, so how many such neighbors of neighbors are there? So each has average k, so that will be k average times k average. Actually, strictly speaking, it's actually k average minus 1, but if k is large enough, we can ignore that minus 1 factor. So it is of the order of k square, right? So because you have k neighbors, and each of your k neighbors has k neighbors themselves. So imagine you have 10 friends. Each of your 10 friends have 10 friends each. So in one distance 1, 10 people, and in distance 2, 10 times 10, 100 people. Okay, that's the argument. So then in a third remove, so in a distance 3, you know k cube people, and so on. So let's say you go up to some distance d. So you basically the total number of people is k plus k square plus k cube plus dot 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 kd, and the leading order of this would be kd. So we can ignore the smaller powers. Okay. So now you are saying that, okay, what is this d? This d is the path length of the network, right? How far do you have to go? So so now essentially you can do it like this. So you can say that, okay, n goes as k to the power d. So log n equal to d log k. Okay, or roughly equal to d log k. Sorry. Oops, sorry. Yeah, and so therefore d equal to log n by log k. So that's the very simple argument. Okay. Now the average clustering coefficient of this is approximately just p. Why is that? Again, very simple intuitive argument. Okay. So what does the clustering coefficient mean? It means your neighbors are also mutual neighbors. So what does this mean? So this means that suppose you now look at this network. So you're asking what's the probability that this triad exists? Okay. So what's the probability that there would be a link between these two nodes? In a GNP ensemble, this is just P, okay? And so therefore, your average clustering coefficient would simply be P, which is, nothing but average degree by n, because you know that n times probability of connection gives you average degree. So it's just average degree by n, okay? All right, so we have path length and clustering. The third property we talked about was degree distribution. So let's see why it is a Poisson, okay? So again, we'll look at the GNP model because GNP models are much easier to treat than others. So let's take up one particular node in the network. So it's connected with probability P to each of the n-1 other nodes. Okay, so then if I ask what's the probability that it's connected to k other nodes? Simple, right? The probability of connection is P times P times P times P, k times, right? You have k neighbors. And you have the remaining ones, or the remaining n-1 other nodes, sorry, n-1 minus k other nodes you're not connected to. So what's the probability of not connecting? 1 minus p. So 1 minus p times 1 minus p times 1 minus p times 1 minus t for all the n-1 minus k. So, right? So that's where it comes from. But now, there are, these k neighbors that you're connected to, that's a particular choice. Okay, how many ways can you choose these k neighbors out of n-1? n-1 choose k, right? And so finally, you end up with the probability that you're connected to k other nodes as n-1 choose k, p to the power k, 1 minus p, n-1 minus k. And of course, this should be a very, very familiar expression. This is nothing but the binomial distribution with mean np and variance np1 minus p. Okay? And now, this is statistics 101. We know that if we take n go to infinity and p go to 0 such that the product remains finite, then this essentially reduces to a Poisson distribution, okay? Where the parameter, the single parameter lambda is nothing but the average degree, okay? And so that's why I said that for a Erdős-Rényi network, in particular the GNP ensemble, would have a degree distribution which is given by a Poisson distribution, okay? Yeah.
Same true for GNL as well?
GNL is much harder.
But do you get still Poisson type distributions?
Okay. Frankly, I don't know. The honest answer would be I don't know. I suspect yes. Okay, very, very surprising if it has some other distribution, but I have no clue how the proof is done. Okay, because the GNL puts in lots of restrictions. It's very hard to prove anything. Okay, so we are running very, very close to the end of the class, so I will try to slightly hurry up. I definitely won't be able to finish everything I plan to say, but that's not an issue. Let me just go to a natural endpoint and I'll stop. Okay, so fine. So until, as I said, 1998, this is essentially what networks meant. Okay, physicists dealt with this, mathematicians dealt with this. Everybody was happy in their own little worlds. And everybody, of course, knew that neither of them are actually anywhere close to reality. Okay? Of course, you can say crystal lattices are kind of like this, and mathematicians would say, there are certain, like this percolation problem, this is not a bad model for that. But most networks that we see around in nature, social networks and so on, they're not either random or a lattice, okay? They have various kinds of structural patterns. And so the question was, how do we capture these patterns? So, suddenly, there comes points when new ideas start coming together very quickly, okay? So that's pretty much what happened in '98. So a paper came out. So I'll basically focusing on macro patterns. So when I say macro patterns, I mean, these are gross structural patterns that are visible in terms of the macroscopic properties of the network. Micro patterns I will not deal with because Shakuntala has already dealt with motifs in great detail. But in the next, well, now it will probably be the last lecture because in the next lecture I'll have to deal with the stuff that I won't be able to cover in today's lecture. I will be dealing with meso-level patterns. So there are these 3 levels at which you can actually find patterns. So today I'll quickly talk about a bit of the macro patterns. And one of these macro patterns was the small world effect. Okay? So what's the small world effect? So let me give you a quick analogy. A quick illustration to mean what do I mean by a small world. So once I was in Frankfurt airport going somewhere, and then some guy comes and sits down beside me with like a big tube which pretty much can only hold a poster. So I kind of guessed that, okay, this guy is going to a scientific conference. Okay. So, and he kind of vaguely looked South Asian, right? So I kind of, I don't remember who initiated the conversation, but we started talking, and surprise, surprise, it turned out that he was Bengali like me, and surprise, surprise, it turned out that we actually have a common acquaintance. Okay. And so we both started saying, oh, it's a small world, right? I mean, fancy the chances that you're sitting in Frankfurt airport and the person who sits next to you is someone who you share a common friend with. Okay? And this experience we have all the time, right? You go to the boondocks and you come across someone, and after some questioning you suddenly find that that person's first cousin knows your whatever uncle, right? And what are the chances that, given that there are actually, what's the current world population? Billion or 9 billion? Sorry? 8 billion, yeah. So, so given that there are 8 billion people on this planet, what are the chances that you meet someone entirely at random and you happen to have a common neighbor? Okay? In a random network, this is like minuscule, right? Given that each person knows about 100 people, so your average degree is 100, so that's the numerator, and denominator is 10 to the power 9, let's say. So the probability that you'll have a node in common is 10 to the power minus 7, okay? Minuscule probability, okay? Nevertheless, this keeps happening regularly. So you know that this probability cannot be 10 to the power minus 7 if it happens so regularly. So the question is why, okay? So now, of course, when you want to do science, you can't just depend upon chance encounters like this. You want to do controlled experiments, okay? So Stanley Milgram was an American sociologist. He's actually a very interesting character, but I have no time to go into the stories about this guy. But there's a very interesting book, a biography written on him called The Man Who Shocked the World. So it turns out that in the sociology, although we know Milgram for this experiment, in the sociological world, he is primarily known for a completely different set of experiments where he basically made unsuspecting people who were drawn for a psychological experiment. So he would basically advertise that psychological experiment volunteers wanted, okay? And then volunteers would come in, typically graduate students, and they will walk in and they will be made to register, and they said, okay, we need you to assist with some experiment. So they were made to think that the experiment is not being done on them, rather they're assisting in an experiment. So what they would do is they would go to a room, and there would be some apparatus with pretty serious looking dials with currents marked on them, and they'd say in the next room there's a person on whom some electrical shock apparatus is strapped. You won't be able to see it, but you'll be able to hear it, okay? And so there would be a person in a lab coat. So they would say that we want to see how much shock can a human being endure. So, so this person in lab coat is like telling him, okay, increase the electric shock. And so this guy is dialing. Of course, what he doesn't know, in the other room, there's a trained actor. Okay, so this guy puts in the dial, and this person is screaming, oh, it hurts. And then the guy kind of probably, should I? And this lab person, yeah, keep increasing. So then this guy increases, ah! And then he says, are you sure you want me to increase? Yeah, sure. Ah! And then this guy kind of, at this time kind of gets a bit scared. Should I keep going? And then, eventually the screams become, louder and louder, and then eventually, it starts whimpering, and eventually the person just falls silent. The actor just falls silent. The implication is that the person is either passed off or dead. Okay, and this lab coat guy is still saying, keep increasing. Okay, so the point is the experiment was not being done on the actor, but on the person who was doing the dialing up. It was to see that how far would people go to do things which they know is killing someone else if they are being told by someone who's apparently in authority. Okay. So the fact that we can, so this was basically driven by the Eichmann trials of that time. So Adolf Eichmann was this one of the engineers of the final solution, the Holocaust. So when Eichmann was, Eichmann after the Second World War had escaped to Argentina, and then he was captured in the 1960s by Israeli commandos and brought to Jerusalem to stand trial. So there's a very famous book called Eichmann in Jerusalem, written by Hannah Arendt on this trial, where Hannah Arendt very nicely, she subtitles the book. The book is called Eichmann in Jerusalem, but there's a subtitle, The Banality of Evil. Okay? So the point she makes is that this was not a monster. If you look at Adolf Eichmann, he's an average Joe. He's like you and me. So what makes it horrible is that an average Joe like you and me can end up killing millions of people, okay, as just a day's work. Okay? So Milgram was basically doing this experiment to show that the engineers of the final solution were not extraordinary monsters. Many of them were just ordinary people like you and I. And under the same circumstances, you and I probably would also do exactly the same thing. As long as we think we are being told by people in authority to do certain things, we would end up doing those things even though we know that we are killing so many people. Right? So he's famous for those experiments. Of course, it's very, very controversial, as you might imagine. The moment he published this, all hell broke loose in psychological circles about the ethics of such experiments and so on. But among non-controversial experiments that he did was this small world or a 6 degrees of separation experiments. So what he did was, he said that, look, I will basically ask people in Omaha, Nebraska, which is about I think 1,000 miles away from Boston, that you have to give a package. You have to make sure that a package that I give to you reaches a particular person in Boston. Now, the thing is, you can't use the postal service. You have to give this package to someone you personally know. Okay? And that person has to give the package to someone they personally know, and so on, until it reaches this particular individual. All right? So, so here you are, starting position. And so then, let's see. So every time it changes hands, you write down, your name and address. And so if it eventually reaches the target, then Milgram will take that package and read off how many hands it changed in order to go from this person to that person. So you will know, like, how many intermediate links did it go through. So, so I don't know whether this is still a thing, but when we were kids, this used to be very common. So we would get a postcard. I think even postcards probably is something that kids today haven't seen probably. So we would get a postcard written, Santoshi Ma has appeared in a dream to me and said that I have to give 10 postcards to people and if it and then all good things will come to me. When you get this letter, please copy this message and send it to 10 other people, and all good things will come to you. If not, curses of 3 generations will descend upon you, and so on, right? So it used to be a thing, right? Still there in the WhatsApp. Okay, so it's a bit like this chain mail, right? So let's say a typical way in which such a package went. So this is Nebraska, and this is Boston. So you can see that it's like, pretty much in the middle of the US. So one of the sources is this clerk in Omaha, and she has to somehow send a package to the stockbroker in Boston, who's the target, right? So how did the package reach this person? So she knew a self-employed person in a town called Council Bluffs, which is in the neighboring state of Iowa, right? And then this person knew a publisher in Belmont, Massachusetts. So you can see that already in 2 hops, it has reached the state at least, okay? And now you think that, okay, fairly quickly it should be able to reach it because they both live in the same state. But this is where the fun of social networks begins, right? So it turns out that now this person sends it to a tanner he knows in the same town, Sharon, right? So you think, okay, you are almost there. I mean, this person must know this person. Well, it turns out that this tanner knows a sheet metal worker in the same town, who knows a dentist in the same town, who knows a printer in the same town, who knows a cloth merchant in the same town, who finally knows the stockbroker. So it basically reached the town very quickly and then spent a lot of time going around the town before reaching the stockbroker. So here, basically, you have 1, 2, 3, 4, 5, 6, 7, 8. In 8 hops, you reach the target. Okay. Now, yeah. That's actually what you're alluding to is an extremely interesting point. So John Kleinberg of Cornell has actually asked the question, how do people decide whom to give the package to? So it turns out that people are not just randomly choosing who to pass the packet to. They are making some judgment as to who is most likely to give the package to, but this requires an enormous amount of knowledge. You not only need to know your friend circle, you need to know the friend circle of your friend. Okay, so that's a huge second order information, right? And presumably also third order information. And so the question is, how does, you think that, this should take much more, like, for example, it went around a bit, right? So typically this is what should happen, because we typically don't know who our friends know, right? How is it that nevertheless, we still seem to make very intelligent choices? So this problem of finding or searches in networks, how do you search an optimal path in networks is a very important topic in computer science. That how do individual agents with a limited knowledge of the network manage to find a globally optimal path? Okay, so this is a non-trivial issue. Like there must be a lot of information which is being processed. Okay.
Sir, during this hop,
yeah,
we are passing the package from source to target.
So in every hop, what is happening is that, for example, this person knows this person personally. Okay, so she's just handing it over by person.
Just say that if the package is with some information, trying to pass it to the target, and we know the adjacent person to look like that. Can the information be disrupted before it reaches the target?
Oh yes. So for example, it could be like, this dentist over here thinks I'm too busy. What do I care if the package does not reach the person? And so many of these chains got actually broken. Okay. So in fact, that's one of the controversial issues with this particular experiment, because out of let me see, how many did he try? No, sorry. Out of the 296 chains that he initiated, only 64 actually reached the target. The rest were broken. Okay? So this is a controversial point, because what Milgram did was he took only the 64 points and then averaged the total number of intermediates and came up with a value which was slightly larger than 5, and from this he came up with this idea that every individual on this planet is linked to every other individual in at most 6 hops. So that's where the 6 degrees of separation things comes from. Okay? But Duncan Watts has pointed out that this is something which is not warranted by the data, simply because he's not taking into account many of the links which were not, so he, there's a bias here. He's only taking into account the chains which were completed. Okay?
Sir, even if the chains are completed, can the packet change during the hop?
Package. Oh, you mean in terms of Chinese whispers?
Yes.
Oh yeah, that of course can happen, but that's a completely different story. Okay, so because the network aspect is, so you're now saying that what is the probability that there is some, probability of, sorry about this, yeah, I'll just finish at this point. What's the probability that there is some probability of mutation of the message during the passing? Yeah, but that's a very interesting point, but that's not so much to do with networks as the dynamical process on the network, whereas what I'm talking about now is basically the structural feature. Okay, so so there's also a kind of a quick ballpark estimation you can do to do this 6 degrees of separation thing. So you remember that in a random network, I said that the average path is going as log n by log k, right? So now if you say that each of us know about 100 people, and the population of this planet is about, I don't know, 10 to the power 10 or something, okay? So then I will get a number, close to 5, okay? So from there I can get a rough idea that, yeah, maybe it would be a number like this. But there's a fallacy here. The fallacy is that in a random network you assume that you know k friends, and each of your k friends know k friends each, so in second order remove you know k square. But in reality, many of your friends that your friend knows are also your own immediate friends. Okay? So there's a lot of overlap. So the question was, if there's so much overlap in social networks, how is it that this random network argument still goes through? Okay? And that is the question that Duncan Watts and Steve Strogatz tried to answer in a paper in 1998, using where they introduced the concept of the small world network. Okay? So I will stop at this point with, this is just a teaser. So in tomorrow's lecture, I will basically start from here, okay? Where I will introduce the small world network and why is it that even though your network may have high clustering, so very, very different from random network. Random networks have very low clustering. So a typical social network has very high degree of clustering, but nevertheless, its average path length can still show log n behavior if you introduce a few long range connections. Okay? So that was a revelatory idea, that a few long range connections can completely change the global behavior of otherwise regular networks. Okay? So that is the beginning of this new era of complex networks theory. 98 is when the revolution happened, which is still continuing today. Okay? All right.
Thank you. There is still 1 minute left. Should we wait? Very innocently came out of my guest house room, locking the door, and then suddenly, I mean, okay, I did not have a very good rapport with them. Sorry. Sometime back, I was very shocked to see them. Then I realized, both of them were good in the same batch.
Oh, yeah.
I mean, they were in university class of their own. Of course, I knew that since coming here in campus, I forgot about it. So I guess. So in the previous class, we had introduced some examples of signal transduction networks. Or I could say protein signaling networks. And we had also looked at this Michaelis-Menten enzyme kinetics, reaction kinetics. We had seen that different proteins in a cell, they can take part in this protein signaling network when they undergo some chemical modification, typically phosphorylation. And then in the phosphorylated form, they are considered to be active agents for catalyzing a cascade of reactions. And we had also discussed this Michaelis-Menten reaction network, and we had particularly derived the rate of formation of product. If you remember the reaction, let me just write the reaction once more. So the reaction was some enzyme acting on some substrate with some rate K on, and the reverse process happens with a rate K off, forms enzyme substrate complex, and then with a rate V, it gives you enzyme plus product. So this product in this language, in our language, this product substrate is unphosphorylated proteins, and this product is phosphorylated protein. Okay? Okay. So this, and we had derived this equation. This is called Michaelis-Menten equation, which is that rate of product formation is given by, so V is the rate at which this complex gives this thing. So rate of product formation is V times total concentration of enzyme multiplied by concentration of substrate divided by some constant Km plus S. And in the case when substrate concentration is very high, then you can neglect this Km and then S gets cancelled, and then you get the rate of product formation becomes V times Xt. Okay? So this is when the substrate concentration is very high. This may not be an unphysical limit to consider, because particularly we will see today that often the substrate is present in a really high abundance in some stage of the cascade. Of course, you understand this, that one substrate in its phosphorylated form would become the enzyme in the next stage. I mean, that is how the cascade goes. So, and if this is substrate concentration is very small, then you can neglect this S, and then it becomes V Xt divided by Km times S. So, one thing to notice here is that, so this happens when S is much less than Km. In this limit, when you have enough substrate in the system, then this tells you that substrate doesn't matter, there is always enough of it. So, this is the maximal rate at which the product can get produced. Okay? Xt is the total concentration of enzyme. So, this apparently tells you that the enzyme is working at saturation. This is how this step, this is another way of saying it, that enzyme is working at its saturation, and since it is independent of S, this is also called zeroth order kinetics. And here in the other limit, this is called first order kinetics. Okay, so this is this equation we had already discussed previous class, but today I will be needing it extensively, so I just wrote it down. Okay. So today I am going to talk about a very important topic in this protein signaling network, that is called robustness. So, in the past two lectures, we were writing down lot of reactions, network motifs and etc. And we had also from time to time we were mentioning that some of the biochemical parameters are subject to cell-cell fluctuations. Now, of course, these biochemical parameters are an important component when we are looking at some reaction networks. There could be some reaction rate, there could be some degradation rate, or some protein concentration. So therefore, if they are fluctuating from cell to cell, then the question arises how the system still functions. Okay, how the system, I mean the network still functions, it still does what it needs to do. So to understand this, there is this concept of robustness was introduced. It says that there is something in the design of these networks such that they can function even without having any strong dependence on these biochemical parameters, particularly those which are fluctuating from cell to cell. So this aspect is called robustness. If on the other hand, there are some properties which actually change, which actually explicitly depend on the biochemical parameters, and they change when you go from one cell to another, then those properties are called fine-tuned. In a same signaling network, you can have some features which are robust and some other features which are fine-tuned. Now, this I will illustrate this concept of robustness for the case of bacterial chemotaxis or chemotaxis network. this particularly this E. coli chemotaxis, which we will consider, it is one of the most well characterized signaling network in biology, and it shows robustness, and as we will see, the robustness is an extremely important design principle, such that if you are trying to come up with some description of the network, let's say some mathematical description, then often you can rule some descriptions out because they are not robust. Okay, so the robustness acts as a very important design criteria. So before I go into robustness and fine-tuned these things, and in fact we will, what I just said, we will also see one particular example today where we will try to understand one particular aspect of the network. We do have a mathematical form which is perhaps the simplest possible form one might develop, and we will show that instead of robust, that description gives us fine-tuned property. So we have to rule it out and we have to go for some other description, little bit more complicated than that, which allows robustness. So before I go into these discussions, so I need to spend some time describing the phenomenology for bacterial chemotaxis. So what is chemotaxis? We mentioned it few times, this word, in past 2 lectures, and maybe most of you also have an idea. It is just motion in response to a chemical signal. Taxis, the word taxis means motion, motility, and chemo comes from chemical. So these bacterial cells, and also quite a few other cells also, many eukaryotic organisms also, they have this ability that if you place them in a concentration, in an environment where there is inhomogeneous distribution of food, let's say, and then you observe them under the microscope, they will try to follow the food trail and move towards the region where food concentration is high. Similarly, if you put them in environment with some toxic chemical, they would move away from that chemical. So there are 2 types of chemicals which can trigger chemotaxis behavior. One is attractant, another type is repellent. The names are self-explanatory. Among the attractant, there are 2 possibilities. It could be a nutrient, or it could be simply, if it is a nutrient, then the bacteria would actually go and metabolize it. Or it could be simply some chemical attractant which the bacteria likes, gets attracted to, but doesn't eat it up. Examples are, for attractant I can have sugar, this is a nutrient, and there are some amino acids, serine, aspartate, and for repellent I have some certain metal ions. Among amino acids, leucine is one example which acts as a repellent. Okay, names are not important, but these are all nutrient. Okay, aspartate, these are nutrient, but you can actually perform some chemical modification of them to bring them into a form which still acts as an attractant but becomes non-metabolizable. For aspartate, the variant is called alpha methyl aspartate. I will not go into the details of exactly what chemical modification is involved here, but this is often an important thing for experimentalists who are actually trying to look at the chemotactic behavior of the cell. The thing is, if you place it in a nutrient gradient, then it is metabolizing the nutrient. So as time goes on, not only it is climbing up the gradient, it is also changing the concentration environment of the nutrient, which can add one more level of complexity. Not that it is never studied, that is studied too, but if you just want to look at, I mean, in a time independent but spatially varying environment, what is the chemotaxis motion it is showing, then it is often considered that you consider an attractant, not a nutrient. So this is one way which is often used, that you perform some chemical modification and make them non-metabolizable. Now, although we will mainly consider chemotaxis for this talk, there are other types of motion also. For example, phototaxis, when the cell responds to some light and moves. It sometimes one can see magnetotaxis, when the cell moves along some magnetic field, or thermotaxis, when the cell follows some temperature profile and tries to localize in a region where the ambient temperature is most suitable for that species. So, but anyway, today we will only focus on chemotaxis. Now, as I said, that chemotaxis, you can think of it like this, that you have some E. coli bacteria and you place them in an environment where there is different concentration of food at different place, and you just observe their behavior under the microscope. You will see they are climbing up the concentration gradient of nutrient or attractant. Now, actually, if you look at the process, if you think of it more closely, it is actually extremely impressive feat which this simple unicellular organism is able to achieve. One thing is, it detects the concentration gradient in a very sensitive manner. Even if you put on some very weak concentration gradient, even then the bacteria is able to sense it. So, one impressive feature is weak gradient detection. Then it can work in a very wide range of background concentration. The background concentration, so the system is like this, you have a background concentration on top of which you are setting up a gradient. So just now we said even the gradient is extremely weak, even then the cell can be seen to follow it. But the background concentration can vary within a very wide range, 3 orders of magnitude. So starting from few micromolar, you can range it up to few millimolar, and the cell will still be able to sense a weak concentration gradient set up on top of that. Okay? So I write it as wide background range. So both these are impressive enough. However, the real shock comes when you actually look at the cell trajectory under the microscope. You will see the trajectory is nothing like, okay, the cell picks up the gradient, then obediently walks up in that direction. Trajectory is extremely noisy. It is a run-tumble trajectory. So I will write it as noisy run-tumble motion. Not only it is sensing a weak gradient, it is not able to swim in one particular direction for more than a second. If it is trying to swim in one direction, roughly about every second, it is completely losing its orientation, and its direction is getting completely randomized. So this is because of the run-tumble motion which the cell uses to move. So this E. coli bacteria, they have this form, they look like this. This length is about 2 micron, the length of the cell body, very tiny, and from the cell body about 10 to 12 flagella come out. Like this. Each flagella are attached to the cell body at their base via some tiny flagellar motors. Okay? Now these motors can have 2 possible rotational bias, counterclockwise or clockwise. So when all the motors rotate in the clockwise direction, then they all form a very nice coherent bundle. So it looks like this. And this bundle then propels the cell forward. This is called a run. Typically a run speed is 20 microns per second, 20 microns per second, and typically a run lasts for 1 second. If you are in an environment where it is homogeneous everywhere, a run will last for 1 second. After every 1 second, what will happen? Some flagellar motors will start rotating in the clockwise direction. When it happens, then this thing gets dispersed. This bundle is not coherent anymore, and then the cell looks like something like, so they are everywhere. They are not able to exert any net force. And however, the cell, that means the cell cannot move. But if you look it under a microscope, you will not see the cell is stationary, static, frozen. No. Instead of, when it is not able to move, it randomly rotates about its own body axis. That is also not a very coherent rotation. So it just randomly rotates this way or that way, like that. It does so for about 0.1 second. This is called state of tumble. So within 0.1 second, it undergoes random rotation, and maybe those flagella which started going in the clockwise direction, now they switch back to their counterclockwise mode again. Again the bundle is formed, and again the cell is moving, but this time it is moving in a new direction because it has completely lost its earlier orientation. Yes?
Ma'am, you said that it runs and tumbles no matter, even if the gradient is like very uniformly. I clearly know that the gradient is increasing in a particular direction. Even then it tumbles?
No. Yeah, even then it tumbles.
So
what I will
yes.
I was coming to that point actually,
Sure,
because what we will see that if it is going up the gradient, then runs are extended.
Right.
So it is tumbling less, but tumbling for sure.
Okay.
Okay.
So is it like when it tumbles, it kind of gets to explore the other directions if the gradient is more?
So that lot of people have debated about. Sometimes it just, yeah, I mean, it, of course, during the tumble, the fact that it is reorienting itself helps, because then it can explore some other direction in case the previous run was not really
the optimal
helping. But on the other hand, one can argue maybe the previous run was already good. So the tumbles are not helping then. Tumbles are actually taking it in a different direction.
Right. Yes.
So why it is doing so, that is often some thing that is not clear.
Right.
But it is true that if you, for example, if you don't allow it to tumble at all, okay, then you can clearly see there cannot be any chemotaxis. For example, it can only go, for example, okay, in the very trivial case when food concentration keeps increasing towards right, then perhaps all is good. But even if you have a sinusoidal profile,
right,
so such that there are different, it needs to really change its direction to locate the peak.
Yes.
So tumbling is extremely important.
Okay.
Okay.
Thank you.
Yes?
Related to what he asked, so I have heard of this gradient descent thing in machine learning. They also have this thing called stochastic gradient descent, which somehow enhances the speed to find the global minima.
Okay, that I'm not very familiar with that.
I was thinking maybe.
So that helps with this. This is done with this run tumble type of algorithm.
No, it's from what I've heard. I'm not sure. It sounds like they don't just go to the steepest gradient, but they also do some stochasticity, add some stochasticity into that. Yeah.
Okay.
Yeah. But in biological systems, it's usually very noisy, dust and those things. I'm not sure. I mean, it's not just a bacteria on a petri dish, right?
No, I mean, even bacteria on a petri dish is complicated enough.
Yeah, but the evolution is for pond.
Yeah, so yeah, why is often a question which is tricky.
Yeah,
so
in
we would
evolution.
focus on how. Okay.
Ma'am, so like you said that that this run length is fixed. So like
Run length is not fixed.
okay, so like
On an average, it is 1
like
second.
from some distribution.
It is?
It is like follows a like certain distribution. So what kind of distribution like it follows?
Oh, so for a long time people believed if you assume that the switching rate, if you put it in an inhomogeneous environment, switching rate from run to tumble, tumble to run, these are not changing with time, then you expect the distributions to be exponential. Run like this, it would be a Poinsot process and the distribution would be exponential. But this I will discuss later, not today, that people, when actually they measured for single cell, they found that distribution is not exponential, it's a power law. So which means long runs are quite probable. Okay. So and people showed that this happens because even in a homogeneous environment where there is no concentration gradient in the environment, the switching rates are quite noisy. And this was not visible earlier because single cell data was not available. People were looking at population and they thought it's exponential. So.
And ma'am, one more thing that you said that like when a cell runs, okay, like then the bundle of the flagella, so that rotates in the in
all of them are rotating in the counterclockwise direction.
So
yes.
like if it if it rotates in the clockwise sense, so like then it can also run, or like there is something like specific about this counterclockwise.
So they have an inherent bias to rotate in the counterclockwise direction, because that is why you see runs are much longer, 1 second. They are generally rotating in the counterclockwise direction unless somebody, this will be clear when I explain the biochemical pathway, the signal transduction network, that generally when these flagellar motors are free, then they are rotating in the counterclockwise direction. It is only when some particular response regulator comes and binds to them, that induces a clockwise bias. Okay, so I will describe all this later. But because it is counterclockwise direction is favored, when everybody is rotating in the counterclockwise, then it is forming a nice bundle. But it never happens that everybody is rotating in the clockwise manner. Only few of them, so therefore it is dispersed.
Ma'am, as you said that all of the flagellas rotate counterclockwise and then few of them started rotating clockwise. So why is it starts rotating clockwise? After anticlockwise, what makes it start rotating clockwise?
Binding of a particular response regulator, which I will describe.
If something comes in the way of this bacteria or flagella, like as it is running, if something comes in the way, what will happen?
Something comes in some physical obstruction.
Yes, yes.
It will reflect. No. Okay. So often, suppose there is, if you put some hard wall. Okay, and in some, you are doing the experiment in a microfluidic channel and you put some hard wall at the end of it. Then bacteria will reach till the wall and then it will get reflected back. It doesn't try to do anything funny there. If there is it is running, but if there is an obstacle, it cannot move, then it will stop moving. And then, okay, so it will stop moving and eventually some bodily random rotation will take place. It will reorient itself and start moving in some other direction. There was a question at the back. Yes. No, you are raising your hand for a long time.
Sorry. Just taking one step back, you said the bacteria can sense up to micromolar concentration.
From micromolar to millimolar.
Micromolar. So I just wanted to understand how much humans can, let's say I spray a DO here, you'll...
How much?
How much a human can sense the concentration? Because it seems like not a very tiny, I mean, it seems quite...
How much human can sense? Humans, they don't do chemotaxis.
No, deodorant, let's say.
Oh, deo.
That's a chemical at the end of the
okay,
day.
Sorry. Sorry, I have to look it up. I don't know.
It seems like humans are much more sensitive to concentration than bacteria. It just seems...
you are saying human can sense something way below micromolar?
Yeah, because the volume is too high. If I spray it somewhere in the corner, by the time it comes there, it's explode the whole region. And definitely this micromolar, I mean liters wise, they can get to...
Okay, maybe that is possible.
Yeah. And the other question.
But here the impressive thing was, impressive thing was the wide background range, starting from micromolar to millimolar, and also it is not legal to compare a human being with a bacteria. Look at the resources they have got. I mean, unicellular organism, no brain, nothing, a very simple circuit which can be drawn on the board. Okay, so therefore human, they are much more, no, I mean, I did not mean to be, they are much more evolved. Yeah. So when they are doing something as impressive as that, that is something that we should take note of. Yes.
Yeah, just was curious about that. And the other question, I think most of them were asking about counterclockwise and anti-clockwise. Clockwise and anti-clockwise. Are there bacteria which do different motion? I mean, run is done through clockwise for some bacteria, and are there some bacteria which do run through counterclockwise?
So there are other modes of motion also. There are some bacteria which, for example, move not via run tumble but run reverse. So they move in one direction, then they reverse their direction. That is one. So then there is also some other bacteria which have only two flagella associated with them. And okay, I don't remember it right now, but so there are different variants of this run tumble motion also. But what you are asking, is it possible for somebody to move? Not that I know of, fortunately.
Yeah.
Any, yes? If the concentration is uniform, then yes, for small time it would be ballistic, and for large enough time, because after all there is no favored direction, so it will be diffusive.
Also, is it possible that the bacteria wants to run, but because of thermal fluctuations in the medium, it has to tumble, something of that sort?
So one thing I know, that while they are running, they also undergo a little bit of rotational diffusion, such that when you are looking at the bacteria, bacterial trajectory, even though it hasn't tumbled, so to speak, but the trajectory shows a very gradual bending. Particularly it is visible for long runs. They are not super straight. They show a gradual bending. So this rotational diffusion, yes, this I know.
Yeah, I had a question.
And also, yeah, sorry, and what you said, of course, if they, for example, if they are moving in a medium which is very turbulent, very, I mean, of course they cannot move in a straight line then. They have to be, they will be advected by the medium. Of course, that is there.
Is that seen in any reasonable biological system?
Is that seen, so bacteria in a turbulent environment? I would say yes, because they are in our stomach. These E. coli bacteria are in our stomach, and they are not experiencing a very serene situation, you know. Sorry, anybody else?
Yeah. Hi.
This bacteria can sense even very weak gradient. So, is there anything, somehow they remember what was the concentration? What is the typical length interval through which it remembers the concentration it experiences?
I have not yet come to that part where the memory of the bacteria, but typically it is, if you are going for a phenotypic way of modeling, I mean, if you don't want, okay, memory part, okay, I'll come to that later, not now. I have not yet talked about the memory. Yes.
So, ma'am, I have a question. So.
No, sorry, he started first.
Oh.
Wait.
Direction or the other? I mean, what if the gradients are like of the same order maybe, and some of, I mean, the bacteria is meant to consume all the food maybe.
So by multiple gradient, you mean multiple chemicals?
Concentrations of the food they are trying to consume.
Same chemical, but different gradient in different direction. Yes. Yeah, it will follow that. But at the end, I mean, if you give it enough time, if the food, if you imagine that it is not effectively changing the nutrient profile. Yes. If you give it enough time, then you will always find that it has gone to the place where maximum amount of food is there. So it can follow different gradients. Suppose there is some lower minimum. Yes. There is still a cluster of cell there, but with low probability. Yes. And where the food concentration is maximum, the cell density is also maximum.
Okay, so it will always prefer the higher gradient.
It will higher gradient.
Yes, I mean to go in that direction.
Okay. So even if, suppose if it so happens that the gradient in that direction is weak, but eventually it continues for a long distance and finally takes you to a place where the food concentration is high, it will follow that.
Instead of going to a greater peak, I mean
It will do
faster
that.
peak,
It will, so few cells will do that also. But if the gradient is weak, then the cell density, the probability distribution of finding a cell at point X, the position distribution of the cell will be proportional to distribution of the concentration, the Cx, the ligand density profile.
So the gradient matters more than the actual peak, I mean the concentration, actual
No,
concentration.
it is following the gradient and going towards the region where, so what will happen that suppose if it is a steep gradient, then you can see, imagine it will reach there faster. But given it enough time, it will still like to go where there is maximum concentration of food. But it doesn't, but it is a very dynamical thing, okay? It doesn't go there and sit quietly. Because run tumble motion doesn't stop just because it has reached there. Okay.
And there is no preference also.
There is no
And
preference?
There is a preference finally that they have.
There is no preference in the run direction. That's what
Right,
you was.
yeah.
Yeah. So after a tumble, it gets completely randomized.
Yes.
So somebody at the back. Who? It's okay. Achha, okay.
No, I was asking, in case of repellent, is it exactly the opposite, like attractant?
Exactly the opposite.
Okay.
Exactly.
And does the motion, it is like a Brownian motion, I mean completely random? It is
But it has some, so to speak, it has some activity.
Okay.
So it is run tumble motion. If you look at its typical some walled lines or typical trajectories, it will look different from just an ordinary diffusion because it is running for some time and then tumbling. So although for after a very large number of run tumble events, if you look at its mean square displacement, it will be diffusive. But in the short time limit, it shows, I mean, quite strongly a very different behavior.
Okay, thank you.
Yes.
Yeah, I was wondering at what length scales is the bacteria detecting the gradient? At the body length scale or at the run length scale? Is it comparing the previous position versus the present position?
It can detect even one nutrient molecule per cell volume per micron. So very weak concentration range.
But at what point? During the run or during the tumble?
At what point?
In these two moves,
Huh.
during the run, is it detecting? And is it comparing between the previous position?
Yeah, I'm coming to that. Hold on, I'm coming to that. I have not yet talked about the detection. Yes.
There was a previous mention about a wall and a bacteria.
Yes.
So what if there is a wall and a bacteria is, let's say, randomly changing directions? Then won't it get stuck for some time when it reaches the wall?
Yeah, it can get
It
stuck. I
won't
mean, if
get
it
reflected
is a hard wall, this is just a simple cell. If it is a hard wall, it will not try to go through that wall.
Yeah.
It will just wait there, and then some tumble will happen, will reorient it, and then it will go again.
So if there are many bacteria, then they can form this thing, MIPS kind of state, right? Where they coalesce together near the walls. Is it also seen in like labs on petri dishes maybe?
By putting some hard. Yeah, no, it is not. Yeah. Okay, so. Yeah, so this run tumble motion I was describing. So yeah, so I have described the motor rotation and okay, so the last point I was talking about is, if you look at the bacterial motion, it is very noisy. It is running and tumbling and going in all possible directions. But nevertheless, after long enough time, it is still able to detect, move in the direction of a gradient, which can be very weak, which can be present over a very wide range of background concentration. Then another thing is, this quite a few of you asked, it cannot read the spatial gradient directly. because the size of the cell is very small, only couple of micron. So no spatial reading. There are some other organisms, some other eukaryotic organisms which are much longer, about 10 micron or 12 micron long. They actually can compare the food concentration between their nose and between their tail. And based on that comparison, they decide which way to go, which way is the gradient, which way should I go. But E. coli is very small. Such a comparison is not possible over such a small length scale. So therefore, what this does, it does something quite remarkable. It relies on temporal integration. This means that it moves, and that is, it runs and it remembers what it has seen along its trajectory. Now, of course, when I say remember, I should put an air quote around it because it doesn't have a brain. So what do I mean by remember? But we have seen earlier that there are several ways, using simple circuits, there are several ways to store a memory. Here also it has a way to store the memory, but anyway, so it along its trajectory, if it finds food concentration is going up, then it extends those runs. On the other hand, if it finds along the trajectory food concentration is going down, then it would quickly tumble and choose a new direction to run. Remember, I emphasize this point, even if it finds that along its trajectory food concentration is going up, it will still tumble. And after the tumble, it will still try to move in a completely random direction. So it is not like it remembers that it was good earlier. So even if I am tumbling, I would continue roughly in the same direction. It doesn't happen like that. After the tumble, it is completely randomized. But the fact that favorable runs are extended and unfavorable runs are cut short makes sure that in the long time limit, the cell develops a net drift up the gradient. This is called chemotactic drift. One thing I should have mentioned, that I told you about this run or tumble is completely determined by the rotational bias of the flagellar motors. Okay, if all of them are counterclockwise, it is running, and if some of them are clockwise, it is then tumbling. So experimentalists have used this fact to their advantage. They have said that, okay, then I don't even need to look at an actually swimming bacteria. I can just take one E. coli cell. It has many flagella, so assuming that it can spare one, I will take a flagella and I will tether it at a point. And then under the microscope, I will simply look at the rotational state of the flagellar motors. If everybody is rotating in the counterclockwise manner, I will say that, okay, the cell is effectively running. If some of them are rotating in the clockwise manner, I can calculate what is the tumbling bias, what is the clockwise bias, what is the fraction of the motors which are rotating in the clockwise bias. So this way, this is very, so often chemotactic response functions are measured like that. I mean, it's not like the experiments are not performed on swimming cells. People are doing that. E. coli is a very well studied system, but many experiments are done on tethered cell, because it's very easy to focus a tethered cell. If it is swimming, you have to track it, but it's a very simple experiment to focus a cell which is not going anywhere and look at the response of the flagellar motors. Okay? So tumbling probability is something that people are experimentally measuring. Yes? Flagella has a very detailed structure, okay, that people have figured out. It has different segments that I am not going to cover here. I can give you some reference. This is all detailed chemistry of what are the different components of the flagella, what are the different proteins that have gone into making it. So this, you can read it up if you are interested. Yes?
So the bacteria senses the gradient during both run and tumble, both phases, or?
No, as I said, gradient sensing, it is something like it remembers what it has seen along its trajectory. So that is that. So during tumble, its motion, its position is not changing. So this mainly this part, sensing part is done during the run. Tumbles are very short-lived anyway. So it is mainly done during the run. It compares, actually more specifically, when I say it remembers, it compares the recent past with the distant past. If the concentration experienced in the recent past is better than the concentration experienced in the distant past, then it concludes that therefore I am heading towards a good region, let me go, keep going. On the other hand, if it is the other way around, that the recent past is not so good, but distant past was better, so then it's clear, right? If your grades in the first semester are very good, but by the time you reach your fourth semester, they are taking a nosedive, then you know that you need to do a course correction. Something like, yes.
Does it depend on how many, does the extent of how much it tumbles, does it depend on how many motors are going counterclockwise, and is there like a typical range?
No,
is there any
no,
control in that?
No. It is when some, because when some, what I mean, when you say extent of tumble, you mean what? Because after every
Theta
tumble,
rotation,
it is
how many
randomized.
degrees?
Sorry?
The rotation, when it tumbles sort of the direction.
You cannot
rotation.
measure it like that because the rotations are completely random. So it's not like it is rotating gradually and when the tumble stops, the rotation stops. So you can measure the rotational angle and say that, okay, it was a, so it is rotating at random and.
So there's no control over the tumble?
No. Yes.
Tumbling time scale, 0.1 second, that is still much larger than the sensing chemistry wala time scale.
Inside the cell? Yeah. I mean, there are different time scales inside the cell. Some of the reactions are quite fast, much faster than this. But there are some reactions, particularly the methylation, demethylation reactions, which are much slower than this. So there are particularly some slow, and that actually plays a very important role in this. Any other questions? Yes?
So when the bacteria decides when to tumble, like if it is going up the gradient, then it always senses that I am going in the right direction. So it should never tumble?
No.
So that
because there is a lifetime for which the motors can rotate. This will be clear when I explain the pathway actually. That you will see that there is some natural events, which, not natural, I mean events which are happening, some reactions, which will actually make sure that it tumbles after a while. Yes.
I think, it's just a comment. I think like, as you said, like there is a rotational diffusion happening. Maybe that also contributes towards motion towards the, while, I mean like even if it is tumbling and then it is moving at a random direction, then we can't predict whether it is going towards a higher concentration, right?
No.
So it should be that rotational diffusion that is happening should contribute to this kind of bias towards the higher concentration.
No. Even without rotational diffusion, particularly if you are considering bacteria in one dimension, which is not an unphysical consideration, because people have been able to perform experiment within microfluidic channel whose width is much smaller than the mean free path. So if it is 20 micron per second, in 1 second it goes about 20 micron. Okay, so and people have considered microfluidic channel which is much smaller than that. So it is smaller than the mean free path. Then the motion is effectively one dimension. Even then it shows chemotaxis. In one dimension motion, there is no point in having rotational diffusion, right? It is either left or right. So, okay, I would like to continue that. Yes, last question. Sorry?
In nutrient-rich environment, you mentioned that the runtime increases, right?
Runtime increases, yes.
But doesn't it make more sense to decrease because you would want to stay in that environment for a
Yeah,
longer
but
time?
it doesn't happen like that. It reaches there, and then there is a, so this is a very different thing. Then there is a competition between drift and diffusion. I don't want to get into that. Okay. But the thing is, it reaches there, then it can, it will also, what keeps it there is that it reaches in the nutrient runtime is large, but suppose it crosses the peak. Okay, suppose there is a non-monotonic, it crosses the peak, but then when it starts running in the wrong direction, those runs will be short. So it will again be, so there is a chemotactic drift, so it will again be moving uphill. Okay, so let us maybe continue for some time. Okay, then there is, so far I was talking about how it uses its run tumble motion to find the food. That is all about sensing. I put a gradient in the system and the system senses the gradient, modulates its run tumble motion and move in the way it is supposed to move. But there is another part in the thing that is called adaptation. So I will just consider this following experiment. That suppose you have a very homogeneous environment, no gradient, nothing, and you have placed there a bunch of cells and you are observing them under the microscope. So the cells are doing run tumble motion happily. Then you add some attractant in the system uniformly everywhere. No, you are not setting up any gradient now, you are uniformly adding attractant everywhere. So now everywhere in the medium attractant concentration suddenly goes up. Now when the cells are running, they will suddenly feel an increase in the attractant concentration along their trajectory. So they will think that, okay, I am heading towards a good region now. So irrespective of which direction they are going, okay, attractant is being elevated everywhere, so they will think I am heading towards a good region now, so let me keep going for some time. And if you, under the microscope, you are measuring the tumbling probability, tumbling frequency of the cell, in absence of any attractant, there was one tumbling frequency, roughly about once a tumble per second, right? If the run duration is 1 second. You will suddenly notice a dip in the tumbling frequency, okay? After some time, the cells, so to speak, realize, again, when I say think, realize, remember, all these things have some specific meaning in the biochemical sense. So after some time, the cells realize that no, whichever direction I am going, it is not changing anymore, right? Now, they suddenly saw a surge. They thought they are heading towards a good region, let them extend the run. But after that, they realized that now there is no change along their trajectory. So now what they would like to do, they would like to bring, then the tumbling frequency start increasing again. It keeps increasing until it reaches the value which was its original value. Okay, so this thing is called adaptation. Not only that, the fact that it reaches exactly at the same level before you had added the stimulus, it is called exact adaptation. This is a very common property, adaptation is a very common property for a lot of different sensory systems, that you give some input, the system responds, but then after some time it relaxes. It relaxes and goes back to its original state. Here there is also another advantage of exact adaptation, which means now again if I do the same thing, again if I put in a step of attractant everywhere, then the cell will do the same thing. So after I give it some stimulus, wait for some time, it has again adapted to the pre-stimulus condition, ready to receive more. Okay, now if I pour in more attractant in the system, the same thing will happen. Tumbling frequency will take a dip and then finally it will again rise slowly back up. Remember, I am saying slowly. I will explain that why it is slow. So slowly it again rises and goes to the level. Now this way you can keep on adding more and more attractant, and the system responds to it. So however, this cannot continue forever. You cannot keep raising the attractant concentration. At some point it will hit the limit of this range of sensitivity. I mean, if attractant concentration is more than few millimolars, then of course the cell will not respond, but over a wide range it still does that. Okay. So now it is time to describe the network. How does it perform all these things? exact adaptation, very sensitive detection, even despite a noisy run tumble motion underneath. How does it manage to do all that? So what is the signal biochemical pathway inside the cell? Any question? Yes. Run and tumble? Sorry, I don't follow. What do you want to do? It is not a Brownian.
I mean, like I'm saying that, is it possible to write, I mean, if I write, I mean, depending on the sort of, I mean, I guess what I can ask is that, is it possible to model this sort of behavior using some sort of a dynamical equation, like a Longeval equation or something
No, that's
of
what
that
we
sort?
will do. We will model it using some dynamical equation. We will do that. So I have not come to the description of the mathematics, which that I will not go to today. In tomorrow and tomorrow's class I will do that. So now it is time to draw the signal transduction network. Okay. So as I said that I mentioned it earlier also, that you have put set up some concentration gradient outside the cell. Somebody in the cell has to be responsible for transmitting that information inside. Only then ultimately the run-tumble response can be modulated. So that is done by chemoreceptors. Should I, maybe I draw it here, yeah. So these are receptors. I need more space on the right. Just 1 second. So what are these receptors? They are transmembrane proteins. Half of them are outside the cell, half of them are inside the cell. I am not drawing the cell membrane here. And these receptors, the part that is sticking outside the cell, can bind to the ligand molecule, and that changes its activity state. The receptors, because just like transcription factors, they are the ones responsible for transmitting the information from outside to inside. So therefore, they are in two conformations, active, inactive. So this in E. coli cell, one actually has very large number of receptor. So maybe I will just, this one I need. So this I can get rid of. So in E. coli cells, there are 5 different types of receptors. So these, which means they sense different types of receptors, means they sense different types of chemicals. Out of these, and these 5 different types, but the total number of receptor molecules is very large, of the order of 14 to 15,000. Very large number of receptor molecules. And there is, among these 5 different types of receptors, there is one receptor which senses serine. Remember, I wrote serine and aspartate, these two things. There is one receptor which senses serine. They are called TSR. Don't even bother to remember these names. It doesn't matter, but I'm just mentioning them. And there is another receptor which senses aspartate, another attractant, that is TAR. And they are actually present in very high abundance. They constitute 90% of the total population. And the remaining 3 types of receptors constitute 10% of the total population. Okay, and since these 15,000 receptors are not just everywhere scattered in the cell, they are actually all very tightly clustered near the pole region of the cell, here. So there is a particular advantage why these receptors show this compact clustering. That is because they show, I mean, people have seen that they have this cooperative interaction, which means they would like, if some receptor, suppose one receptor binds to the ligand molecule, it is an attractant molecule, and it switches its activity state, because that's what the input molecules do, right? So they switch their activity state. Then it would also like to have the neighboring receptors to change their activity state and have the same activity state as this one. Okay? So there is one very clear advantage of this kind of cooperative signaling. It can generate a huge signal amplification. Remember, just from one binding event, lot of receptors are changing its activity. So the one binding event is actually getting amplified. Signal is being amplified. This is known to be one very important reason behind this very sensitive detection of concentration gradient shown by the cell. The clustering, the strong cooperativity makes sure that, and otherwise it would have been that out of 15,000 receptors, maybe one changes their activity. It would be difficult for the cell to detect. But here, because of this cooperative interaction and because of this tight clustering, it makes sure that changing of one activity state actually gives rise to a lot of subsequent changes that is responsible for signal amplification. Okay. Now, when these receptors are active, in the active state, so sorry, another thing, these receptors are here in the pole region of the cell, and there is some protein which is called adapter protein, KW. By the way, there are many important proteins which are part of this chemotaxis network, and their name starts with CHE, these three letters. They go for chemotaxis. Okay. So KW is an adapter protein which actually clips these receptors which are fixed in the membrane to another kinase called KA. Okay. When the receptors are active, in the active state, they cause phosphorylation of KA. So KA becomes KAP. Then KA is active. It will then phosphorylate another protein called KY. So KY will go to phosphorylated form KYP, and this will be aided by this KAP. In fact, what KAP does, it donates its phosphate group to KY and phosphorylates it. Okay. And of course, the reverse transition is also possible. There is another protein, KZ, which makes sure that this is also dephosphorylating. Anyway, in the phosphorylated state, KYP will go to the flagellar motors. Which were rotating in the counterclockwise direction. It will go to the flagellar motors and it will bind to them. And in the when that happens, flagellar motors start rotating in the clockwise direction and the cell tumbles. So therefore, active receptors give rise to KAP, which phosphorylates KYP. It is the response regulator protein, and it then the cell, this is run and tumble. So this is the response part of the system. Action of, when there is no attractant present, action of KAP and KZ makes sure that KYP concentration is holding steady, not changing with time, such that the cell has its steady state tumbling bias of roughly 1 tumble per second. Okay. Now what happens if I switch on some attractant or repellent in the medium. So I call it stimuli. So this stimuli, sorry, not this way, this way. So this stimuli which is present outside, it could be attractant or some toxic material, it binds to the ligand. If it is attractant, this is important, if it is attractant, then it changes the, it actually lowers the activity of the receptor, which is something different from what we were saying. We were always saying that, okay, some input signal comes, it brings it to the active state. But here that happens only for a toxic chemical. But for a good nutrient or attractant, receptor goes to the inactive state. Let's carefully see what is the effect of that. If it is inactive, then it cannot phosphorylate KAP. KAP is not forming. So therefore, KAP cannot catalyze this reaction. QIP is not forming. And therefore, it cannot go and bind to the motors and the cell swims smoothly. So in presence of attractant, I have long runs. This is the biochemical reason for that. At the same time, if I have a repellent, then the exactly opposite thing happens. That is the scenario I had described. It is active, KAP forms, QIP forms, it binds to the motors and increases their tumbling clockwise bias and the cell tumbles. So this is a very clear reason why presence of attractant gives rise to long runs, presence of repellent cuts the run short. Okay. And also, yeah, another thing is, remember all these things are happening near the pole region of the cell, because receptor is fixed here, and then here it is through this adapter protein, it is clipped to or stuck to this key A, and key A is phosphorylated. So this key A, when key AP gives its phosphate group to QI, that happens here near the pole region of the cell. Then that phosphorylated QI has to diffuse through the cell cytoplasm and come and bind to the these flagellar motors. That takes some time. That takes about 0.1 second. And that is the time that the cell needs to respond. So if you actually look at a, I mean, going back to that experiment when the, I have suddenly added more attractant in the medium, then if I look at how long does it take for the tumbling frequency to dip, that is of the order of 0.1 second. And that comes because of the diffusion time of phosphorylated QI through the cell cytoplasm. Okay, but that's not the complete story. Not only it dips, it also goes back up. So how that happens? So for that I have to bring in, sorry, so here I have written not response, let me call sensory, that would be a more correct word. So this is the sensory part of the reaction pathway, that you give some stimuli and through this pathway the run-tumble motion is modulated. So this is sensing. The next I will describe adaptation. So each receptor has exactly 4 sites. You can think of them as buttons. If you press those buttons, then the activity of the receptor goes up. Actually, it means that there are some 4 sites on each receptor where a methyl group can come and sit. And when a methyl group, so therefore each receptor can have between 0 to 4 methyl groups. Okay? When the number of methyl groups are larger, the activity of the receptor is also higher. And if methyl groups are shorter, the activity also is low. So these receptors get methylated by an enzyme key R, which adds methyl group to the receptor, provided its methylation sites, not all 4 are taken. If it is completely methylated, then KR cannot do anything. So KR adds the methyl group to raise its activity level. there is, so of course, as you can see, if there is a methylation reaction, there has to be some demethylation reaction also. So here comes the most interesting thing. There is another enzyme, KeyB. It goes to the phosphorylated state, KeyBP, and in the phosphorylated state, it demethylates the receptor. So therefore, the reverse movement is also possible. And this, how this is phosphorylated? By the same agent, KAP. So therefore, KAP donates its phosphate group to KY as well as to KB. KB, after receiving its phosphate group, becomes KBP. It goes and demethylates the receptor. Now you see a beautiful thing, that the adaptation, or how adaptation is taking place through negative feedback. That will become clear from here. And this is important, okay? So stop me if you don't understand anything. So suppose the receptor is active, okay? Then everything goes smoothly, KAP is formed, KBP is formed, KBP demethylates the receptor and lowers the activity. If methylation is raising the activity, then removing the methyl group will lower the activity. So active receptor will get, because of this demethylation, the activity will be lowered. If it is inactive, then KAP is not formed, then KBP is not formed. So therefore demethylation stops. But under the action of KR, it is all the time getting methylated. So its methylation level keeps going up, raising the activity. So this is the reason why if activity goes down or goes up, this demethylation-methylation network makes sure it goes back to its previous state again. This part of the sensory network is called adaptation. So there are two parts, sensory adaptation, sensing adaptation. They are coupled via this quantity, and they are getting their phosphate group from here. This still does not explain. So as you can see, adaptation is, it involves, it engages the concept of negative feedback to make sure that the activity of the receptor doesn't become too high or too low. But it still does not explain what I said last, the concept of exact adaptation. Okay, I can see that this way I can actually raise it or lower it. But how do I make sure that I go back to the exactly same pre-stimulus state? That is still not clear. For that we have to, so this is the diagram. Now based on this information, I would like to come up with some simple description which will allow me to show exact adaptation. And as we will see there, we will have to use the principle of robustness. Any question? A few other points. This compared to the very high number of receptors which are present in the cell, the concentration of KR particularly is very low. There are about 140 to 150 KR molecules in the entire cell. And also KB also not as low as KR, it's significantly higher than KR, but even then this is also low, not as high as the number of receptors. So these methylation, demethylation reactions are also very slow. So these methylation, demethylation, these things happen very slowly. The reaction rates are very slow. They are almost 100 times slower than all the other reactions which are taking place in the system. So as a result, when I suddenly add some stimulus in the medium, there is a quick dip because of this sensory part, but then there is a slowly it creeps up to the level it was there originally. So therefore, the adaptation part, the recovery part is often slow. Any questions? Yes. No, tumbling frequency, because it is running for longer time now. Runs are extended, so the tumbling rates are lower. Okay, so the last 15 minutes or so, let me now try to derive the condition for exact adaptation. And here we will see that this thing that we mentioned, fine-tuned versus robustness, that will become important. So, okay. So I start with a model for exact adaptation, and so this is a diagram, and what I will try to do, I will try to use the simplest possible description and impose the criteria of exact adaptation and see what I get, what is the condition I get. So let me say that receptor X, you see that this receptor with key W and key A, this whole thing is often called the receptor complex. Okay, so if you see this word, I mean, it means receptor only, because what people talk about receptor complex is getting methylated or demethylated. But there is no methylation sites here or here. The methylation sites are sitting in the receptors itself. So anyway, so I say that the receptor can be in two different states: methylated, unmethylated, or methylated. I don't care about multiple methylation sites. Right now, it's a simple description. I say receptors can be in two different states: methylated or unmethylated. Unmethylated receptors, X is always inactive. Methylated receptors has some activity, and it has activity A naught. Each methylated receptor has some activity A naught. Next, I assume that key R, this enzyme, works at saturation. That is because this condition is satisfied. S, what is S here? Receptors. Because key R is acting on the receptors and methylating them. So S is the receptor, and as I said, receptors are present in high abundance. So therefore, this condition will be, this means that key R is working at saturation. So I assume key R is working at saturation, but key B is following the first order kinetics, which is okay. I mean, key B, although compared to key B, concentration is not as high as this, but compared to key R, key B levels are significantly higher. And let us say key R works on saturation, and this rate V, it is VR. So, okay, so let me write it, then you will see. This is dxm dt, the rate at which xm concentration is changing. So how can it change? Xm is methylated. So it can increase if unmethylated receptor is getting methylated. But that happens, that is the 0th order kinetics. So that happens with a rate VR times R. R is the concentration of key R. Okay? And how can it decrease? Because of demethylation, which happens with a rate VB times concentration of key B times XM divided by K plus XM. Exactly what I have here, the full, this one. This equation is clear to everyone? Just, I mean, I have written down this thing. So this in steady state, this should be 0. So then in steady state, the fraction of concentration of XM is K VR R divided by VBB minus VRR. This is the concentration. What is the steady state activity? A naught, that is just small a naught times xm. So this is the activity per receptor, and if xm is the total concentration of the receptor, then the total activity is a naught times xm, and the tumbling frequency is just something that we measure experimentally, is a function of a naught, total activity. Okay. So now imagine that I put in some attractant in the system. Then after attractant is added, what happens? Receptors bind to the attractant, their activity is lowered. So now instead of A naught, I assume activity per receptor becomes A1, which is less than A naught. Okay. So the and also when the activity is low, then the demethylation rate will get affected. Methylation rate will not get affected, but demethylation rate will get affected. So I assume that instead of Vb, now it is demethylating with a rate Vb primed, which is less than Vb. Okay, so now I have the steady state value of xm, it is xm primed. After addition, before that, immediately after you add the attractant, now xm takes a long time to change, because how xm population can change? Through methylation or demethylation, which are slow processes. So immediately after you add the attractant, activity becomes A1, which is equal to small a1 times xm, which is less than A0. So this explains the dip in activity immediately after adding the attractant. But now, after you have waited for a long time, system has reached steady state once more, then the new xm primed is same form, but Vb primed is used now, kVRR by Vb primed B minus VRR. Okay, and A2, the new steady state activity, post stimulus steady state activity, is A1 times xm primed, which is equal to just A1 times this quantity. Okay. Now what is the condition for exact adaptation? A naught is equal to A2. This is because I have exact adaptation. So therefore, if I put A naught is equal to A2, this is the condition I get, that A naught k VRR divided by KBB minus VRR should be equal to A1 k VRR divided by VB primed B minus VRR. So this condition, you see, it depends on lot of biochemical parameters. It depends on A naught, A1, it depends on VB, B, VRR, all these. If one of them changes, then the condition will be changing. So to see some examples using some numbers, this is the last thing I will do. I still have about 7 minutes, right? Okay. So yeah, I'll just stop after doing this. So, okay, since I will not be needing that today, so let me now get rid of this. So suppose now let's put in some numbers. Suppose A naught is 10 and A1 is 1. So after adding the attractant, the activity of the receptors are reduced 10 times. Okay. And for simplicity, let us assume K is equal to 1, VRR is equal to 1, and VBB, let's say VBB is equal to 2, just some numbers I am putting in. Then A naught, if you calculate the pre-stimulus activity, A naught is A naught times K VRR divided by VBB minus VRR, which is equal to 10 times 1 into 1, 10, divided by 2 minus 1. So this is equal to 10. What is A2? If you put it in this equation, then you will see that VB primed should be 1.1. So to check that, let us see A1 K VRR divided by VB primed B minus VRR. This is equal to A1 is 1 now, 1 divided by 1.1 minus 1, that is equal to 10. So exact adaptation is satisfied, because I mean, of course, I mean, I use that criteria. But now suppose in another cell the concentration of key R changes by 20%. This is a very reasonable assumption, because key R is present in such a low concentration that even if there is, I mean, 1 or 2 molecules are off, I mean 1 or 2 molecules are more or less, then the concentration will change by a significant, and key R is actually the most important source of fluctuations, by the way. So suppose R changes by, R decreases by 20%. So then VRR, here it was 1, but VRR becomes now 0.8. So then I get A naught is equal to 10 into 0.8 divided by 2 minus 0.8, which is 6.67. And if I use the same condition for VB primed, same value for VB primed, A2 becomes 0.8 divided by 1.1 minus 0.8, that is equal to 2.33. So I lost the exact adaptation. So I have to, for one cell, I find the criteria which gives me exact adaptation, but in a different cell with a slightly different biochemical parameter, that condition is not satisfied anymore. So therefore, this is a fine-tuned property of the reaction network. I'll stop here. If you have any questions, I can answer till 4. But after that, in tomorrow's lecture, I will derive another, I will derive the another mathematical description which will make this property robust. Okay, any questions? What? Oh, exact adaptation means you put some attractant or repellent, activity of the system changes or tumbling probability changes. It increases or decreases based on the type of the chemical that you are putting in. But if we wait for long enough time, then it will come back to exactly the same value it was before you added anything. So not only it adapts, it shows exact adaptation, that it comes back to exactly that same value. Two different conformations of the receptor. So in the active state, it can cause this phosphorylation reaction, etc. Activity specifically, activity means probability to find the receptor in the active state. Because you see, when you even, these are very highly non-equilibrium dynamical systems. It is not that some attractant added, all the receptors obediently goes to the inactive state and sit there. It's not like that. So it is just that addition of some stimulant, nutrient or attractant increases the probability for a receptor to be in the active state. In fact, in the tomorrow's class, I will explain in more quantitative terms what I mean, that I will actually write down some expression for free energy between the active state and inactive state. And after I do that, this will mean that adding receptor makes the active state free energetically more favorable. And adding toxic chemical makes the inactive state, I am saying the opposite thing, adding attractant makes the inactive state energetically favorable, but that it is the other way when you are adding some repellent.
Just last part. I mean, here the receptors are at the tip of the
At the pole of the cluster,
at the pole
cell,
of the
yes.
cell. However, the flagella are at the other end of the cell, right?
No, flagellar, when the, I mean, flagellar base motors are everywhere. It's not like they're at the other end. But you know, when these are long flagella, so when they are actually bunching together, they form one bundle which is in the direction opposite in which the cell is going. Because that is why it is pushing, giving the propelling force. Okay, unfortunately we have a sharp cutoff, so we cannot take any more questions today, but tomorrow, day after. Okay, fine. Yeah, otherwise tomorrow, day after, or in the tutorial maybe, one of these 2 days you can ask me.